What's interesting about life is that despite the revolutionary leaps in cosmology and physics in the last century alone, we're still left wondering how we got here. How do we fit inside nature's deepest laws and across the most vast stretches of time? Where did we originate in this story unfolding across billions, possibly trillions of light years, across billions of years? And how, out of the Big Bang, did we get here? To this point in time where we could turn around and ask about our origins. How did we come to be? How did quantum fluctuations and primordial hydrogen and dark matter halos, how did those interact to ignite the first stellar fusion in the universe and end the cosmic dark ages at the beginning of time? How many nearby stars show signs of habitability? And could these star systems be home to alien life? These are the foremost priorities of the James Webb Space Telescope. And tonight, we're taking a deep dive into what we've already found out there, and the surprising number of questions we still have yet to answer. Hey guys, this is Rich here, and I just wanted to take a second and thank you for watching. And can't really express enough how revolutionary this telescope is. And so I hope I do a good job of bringing you along on the journey that Webb's taken and is currently on. So go get comfortable. Go grab a drink or a snack, find a comfortable place to sit, and let me take you on this journey exploring the most ambitious, technologically advanced, expensive space telescope humanity has ever built. On Christmas Eve of 1968, after a nearly 3-day journey across 250,000 miles of space, and in a capsule the size of a bathroom, 3 astronauts, Bill Anders, Frank Borman, and Jim Lovell, became the first ever humans to orbit another world. Although this 3-day journey took them further than any other people in history, once they got there, their entire trip consisted of just 10 brief circular orbits around the moon in a less than 24-hour period. Now, their main goal during the brief rendezvous with the moon was actually to take detailed photographs of the moon's rolling terrain below. It was to spot any promising sights for Apollo 11's crew. So it's understandable that Bill, Frank, and Jim were completely occupied with getting as much data as possible about the moon's surface and the terrain and any anomalies they might run into that they hadn't been able to spot from the Earth. But as the spacecraft emerged from the far side for its 4th pass around the moon, the crew looked up and witnessed an Earthrise. Look at that. That's their view from the moon, looking back at Earth, looking at the only thing humanity has ever known. It's all there on that blue marble, all able to be hidden behind your thumb, held at arm's length. This mission was almost as famous as Apollo 11 itself, just because it achieved so many firsts. The first time humans had truly left the planet, way beyond low Earth orbit. First time we'd seen the entire planet Earth. First time we left the protection of Earth's magnetic field and entered the complete influence of another world's gravitational field. But maybe the first that was most symbolic of what humans had just achieved was that after 4.5 billion years of evolution, probably millions of years of curiously observing the bright moon dominate Earth's horizon, intelligent beings were now witnessing their own planet's surface from behind the moon. Earthrise would go on to be Time magazine's greatest photos, one of their greatest photos of the 20th century. And notable nature photographer Galen Rawle described it as the most influential environmental photograph ever taken. It showed Earth as a small orb glowing bright blue against the nothingness of space. Lovell recalled that, quote, "It was beautiful. It was the only thing in the whole universe that had any color." The immediacy of this image, Earthrise, in its complete reversal of the only perspective humans had ever known, clearly had a potent effect on the imagination of the world, too. And so did the space-age fiction that was birthed by and around the same time as this. Think of Gene Roddenberry's Star Trek, created in 1966, just 2 years before. It gave TV viewers a pretty realistic idea of where deep space exploration of our galaxy might actually lead. And then a decade later, a man named George Lucas comes along. But Lucas's world was much more grounded in archetypal elements. It has fantastic and science fiction elements. You have aliens, but Yoda plays the role of a wise man, as androids and robots, but they play the role of a jester. Very archetypal elements. So Lucas was still tapping into both sides, and a fantasy where you had samurai warriors, medieval knighthood, you had spiritual magical forces and powers, you had dark evil, cape-wearing galactic nemeses, and all these swirled into a beautiful narrative that would undoubtedly be captivating for anybody, and especially children growing up in a society doing the achievements through science and technology that Western culture was doing at the time. Children seeing men walk on the moon, that's unimaginable, and it's very easy to imagine that in combination with these archetypal characters that are memorable just by their nature would resonate deeply in the minds of children. And this brings to mind a interview I watched of Elon Musk, a 21st century pioneer of spaceflight in his own right, where he mentions he was asked about movies that might have influenced him, and he mentions the first movie he ever went to see in a movie theater was none other than Star Wars: A New Hope. It came out in 1977, I believe, so he would have been pretty young, but he says he can, well, here, I'll play the clip.
You have a favorite movie ever?
I suppose it would probably be like the original Star Wars. Part of it is like that's the first movie I ever saw in a theater. I think I saw it at 6 years old, something like that.
Whoa.
So it really made an impression. Maybe that's why I like space stuff. I remember it being like super wow. First of all, I never, like I said, never been in a movie theater before, and or at least not that I can remember. And so imagine seeing like the first movie that you ever saw in a theater was Star Wars.
6 years old, do you remember it like that?
Yeah, I can remember. I can visualize coming out of the theater.
And I bring that up because for George Lucas, he was also well aware that the hero's journey he molded his story around tapped into a deep desire within our DNA, the human DNA, not just American culture or 21st or 20th century humans. He knew it elegantly fused elements of our mythical past and the grand technological visions of the distant future. Luke Skywalker, his main heroic character, was embodying the idea that you gotta have faith in humanity despite the absurd reality of a nuclear arms race amongst two equally powerful nations now that until we went to the moon were in a a space race that transitioned into more of an arms race. Luke taught them to look to the stars, just like we were all encouraged to do when we saw that first footage of Neil Armstrong stepping foot on the moon, a human on the moon. And that gave us hope. Stories like Lucas's and Star Trek, and real stories of us going to the moon, splitting the atom, unfolding before our eyes. These were absorbed together in parallel. And I think these dreams that civilizations thrive upon, they put us in direct contact with how our common ancestry on this singular pale blue dot of a planet, in some obscure average planet around an average star in an average, well, maybe not so average galaxy. We'll find that out later. But still not extremely unique galaxy. They put that into perspective, that origin, our common origin, vastly supersedes any of our tribal distinctions. Now exactly 27 years to the week of Earthrise, and with visions of seeing the next generation's great frontier beginning to fade out, one lead figure in charge of a $10 billion scientific mission put his reputation on the line and made a bold decision. Astronomer and then director of the Space Telescope Science Institute, STSCI, Dr. Robert Williams, gave the command for the most advanced space telescope ever made, silently awaiting its instructions 400 miles above to deliberately stare into an abyss. But Dr. Williams hadn't taken the gamble alone. He and his team, they'd made a calculated risk. They'd specifically chosen a pinpoint patch of sky. It was known to be void of light. It was actually one about the size of Roosevelt's eye, on the back of a dime, held at arm's length. You can imagine how tiny that is on the sky. Williams had gambled a huge portion. See, directors, they get a pretty significant number of hours to declare what they want that telescope to observe. And so he gambled a huge portion of his specific time, his discretionary time it's called, because he wanted to look into the unknown. He wanted to continue to push the frontiers of exploration. And there was a huge chance he'd fail, and there was a lot of people pushing back, trying to make him doubt himself. But Williams, the reason I'm talking about him is because he had a vision and he had the courage to stick to it and see it through. And he'd been placed in charge of the newly repaired Hubble telescope at this point. We'll touch upon that a little bit later. And so he wanted to put it through its paces. He was a true scientist, which is rare when you get a true scientist merged in a managerial position of authority, to actually stick to the values of science, which is research, preparation, hypothesis, experiment, and then subjection of the results to further analysis and peer review and continual adjustment in accordance with new observations, new evidence. Hubble would be instructed to stare at one spot, this one small spot, for hundreds of hours. But as this long exposure mission went underway, no one knew for sure what we'd see. The critics expected nothing because they were assuming we'd be looking far too deep into the past, meaning there hadn't been enough time yet for anything to evolve. They thought the primordial hydrogen gas of the early universe would have still been way too diffuse from early inflation, which we'll talk about that too. We'll talk about most things in the universe, it turns out, in this very long video. They thought it wouldn't have had time to collapse even into the first stars. But others were just as curious as Williams, and like him, they guessed correctly. After 100 hours of focusing on the same small, empty speck of night sky, collecting any visible photons falling onto the smooth, unblinking 8-foot eye, a swarm of faint objects began appearing. Astronomers had discovered that this small abyss was gazing back at us. Look at that. These are billions of light years away, and billions of years back in time. So what this means is that at an age that some thought would be completely void of stars even, the universe was already aglow with fully formed galaxies. They were bathing the cosmos in light. And there weren't just a few, there were literally thousands of galaxies popping up in the image. The faintest light from these images was nearly 13 billion years old, so they were emitted from galaxies that were in their adolescence 13 billion years ago. And with the expansion of space, they're now 25 billion years, light years away. And that's another thing that we'll be talking about on our journey. The naysayers had been left speechless, but even those who had anticipated something, they were completely baffled at the sheer volume of galaxies that revealed themselves to Hubble. The universe at this early age, not only was it not really expected to have anything in it, but it wasn't supposed to have evolved fully mature galaxies that we are seeing. This was a massive breakthrough in our understanding of the universe. And it wasn't only for the astronomy community. The wider scientific community that was stunned by the deep field images was trying to process this too. Because what did it mean for physics? What did it mean for chemistry and biology even? So the Hubble Deep Field image and its successors were another profound image, symbol, representative of how science and the vision that motivates it can reformulate our understanding of our entire place in the universe. Now fast forward another 27 years, and it's time for the next generation of scientists to breathe new life into our desire to explore the unknown. And in the early spring of 2022, that's exactly what happened. Astronomers excitedly beamed up the same coordinates Hubble received during its 2017 follow-up mission to its prior deep field surveys. These coordinates, they weren't beamed to Hubble, though. These coordinates were sent far beyond low Earth orbit, 400 miles above Earth, beyond the moon even. These were sent into deep space. They were sent to a telescope over 6 times larger, 250 degrees colder, sitting 1 million miles further from Earth, and with instruments 100 times more sensitive than Hubble. This telescope orbits in a place so remote that commands from Earth, even traveling at the speed of light, 670 million miles per hour, still take more than 5 seconds to reach it. Here at a precisely balanced point between the Sun and Earth's gravity, called Lagrange Point 2, we find the James Webb Space Telescope. No, but for real, this is the James Webb Space Telescope. Webb's 21-foot wide, deep gold cryogenic mirror segments. They're nestled safely behind 5 reflective sheets thinner than a human hair. And these sheets of foil make a massive sail that stretches almost 70 feet out so that it fully shields all the precious optics and the instruments from the raw radiation of the sun sitting just 10 feet away and 600 degrees hotter. Since before Hubble had even launched in 1990, astronomers had actually been planning this new state-of-the-art telescope. And by the time it was finally ready to launch, over 30 years later, in late 2021, there was only one chance at success for this $11 billion mission. So naturally, the stakes were high. But to cut to the chase, save you guys a couple hours, on Christmas morning of 2021, after 2 decades of development and multiple near cancellations, the only telescope ever explicitly designed to reveal the first light of the universe, the cosmic dawn, was successfully launched into deep space. And 6 months later, after it went through testing and calibration of its instruments and very, very meticulous unfurling, the world got our first tease of what's to come with the first ever operational image of the universe taken by Webb. Just look at this. Look at the transition between Hubble, the SMACS J0723. It's a galaxy cluster as it appears 4.6 billion years ago. So it's far, but relatively nearby as far as clusters go. But there's a lot of interesting things here. Probably the most fantastic aspect of them is the gravitational lensing going on in the background. Just look right now at the transition between what Hubble and what Webb is able to do. And keep in mind, the original Hubble Deep Field was, like I said, Franklin's eye held at arm's length. Well, this image right here, SMACS J0723, is a grain of sand held at arm's length. And that's what's inside that grain of sand. And just look at Webb's clarity, the resolution that's showing up. And not only that, just look at how many more faint galaxies emerge from the blackness, the black background, transitioning from Hubble to Webb. So the combined mass of this cluster, and the cluster is the main galaxies that are probably the largest you're going to see in this picture. They're much closer than the smaller, redder galaxies in the background there. And they act as a gravitational lens. The light from the more distant galaxies directly behind the cluster are actually bent. And given our specific perspective in relation to this galaxy cluster, galaxies that are right along the line of sight of that cluster, but behind it, are warped and bent around it. And just like looking in a funhouse mirror, how a distorted curved mirror can make really stretched out, arcing shapes, the same thing is going on in these pictures here. There's clear examples of mirroring found in the prominent orange arcs to the left and the right of the brightest cluster galaxy. And we're going to break this down. There's some papers we're going to be looking at later where it explains how there's actually multiple images. There's mirrored images, and sometimes there's triple and even quadruply lensed galaxies. When there's 4 and they lend so that they create a cross, it's actually called Einstein's cross. And this has been seen, and we're going to look at a couple examples of this later. But it's amazing that you can have such a bizarre effect happening on the scale of billions of light years. These galaxies are, hundreds of thousands of light years across. The clusters are spanning millions of light years. The distances are spanning billions of light years. And these events are happening on the scale of billions of years. Light is stretched as it's traveling, as it's emitted from the distant galaxies, traveling through and around and being distorted and bent by the clusters that it travels through on our line of sight. And this image here is what we are seeing right now in our place and time in history. So not only is it a beautiful picture, but it's also packed full of data that's going to help us understand more about the universe. So although it's not going to be on the record for long, as of late 2022, probably it's long, it's of course going to be 2023 at least, if not later, depending on when you see this. This is the highest resolution infrared deep field ever released. The image reveals thousands of galaxies in just a tiny grain of sand. I think it's something like the head of a human. If you look at a human standing a mile away, the size of their head is about the size of the field that all these galaxies are fitting in. As we stand on Earth and look up at night. Can you imagine that? Just how many galaxies there are out there, if in that tiny little portion of the sky, there's this much packed into it. I was trying to make a point in that intro there that we really live in a supremely special time. And the more I learn about history, the more I realize how often it is that people get complacent in their understanding about the universe. Copernicus in particular was, he's the prime example of ripping our paradigm open. He completely removed the Earth from the center of the cosmos. And he had the courage to, at least write the book. I believe he waited until he was on his deathbed to let anybody see it. But it changed it changed our future. These discoveries, then we had Einstein, then we had who overthrew Newton, who dominated the universe for hundreds of years. And now there's physicists out there talking about potentially having to at least modify, if not overthrow, Einstein. And we're not going to know whether we need to do that unless we make observations. And some of these telescopes, on top of the James Webb, there's telescopes being built on the ground that are, think about this, they're larger than the Colosseum. They're larger than a stadium built in one of the largest metropolises in the ancient world. Hundreds of feet across, of, precision polished down to a nanometer mirrors looking up into the heavens. And then we have this technology nowadays to be able to fix, it's called adaptive optics, where it corrects for any atmospheric distortions caused the light to flicker and flitter from the stars. The things we're going to discover with Webb and the whole next generation of telescopes that it's ushering in aren't just going to fascinate and astound us. They're going to really potentially revolutionize our understanding of the heavens. And with that revolution comes a revolution in how we're able to interact with the universe, in the matter within it, in the energy that allows civilization to thrive and flourish and spread out into new planets and eventually new star systems. And with energy abundance comes social change, comes progress, comes the liberation of people from, the drudgery of 9-to-5 work. So these massive physics projects have a much more practical value to them than most people stop to consider. And I think, even beyond that practical value, although because it is delayed for generations sometimes, there's no immediate next quarter return on investment. There's, of course, still a political and economic interest in Webb, but the deeper pursuit of knowledge and knowledge that illuminates our place in the cosmos, I argue, it's the fundamental motivation for all the thousands of scientists and engineers and managers and politicians that worked to get this thing built over the last 3 decades or so. NASA itself actually described Webb as, quote, one of the most technically ambitious and complex missions it's ever undertaken. And it's possible only the Apollo program is comparable in terms of just how ahead of its time the technology was. The Apollo missions, they not only took humans to the unimaginable frontier of the moon, but allowed them to drive essentially a dune buggy on its surface. Think about how much of a leap forward in progress that was. From 50 years earlier with the invention of the airplane, humans had not flown in the air. And then 50 years later, we're on the moon driving around on a lunar rover. I think it might not be matched again for a long, long time. But Webb certainly comes close. And the technology of Apollo was decades beyond the pace of where it otherwise would be if it hadn't been pushed. Like, what it means is NASA actually had to develop their own technologies. They had to outline a plan of what they needed to do and accomplish, what sort of technologies they needed to make that happen, and then look in industry and third parties, businesses for that, and if it didn't exist, throw money at it until you had a working version of that technology. And that's almost exactly what the team over the last 3 decades, what they did for Webb. It's very similar. In 2002, when NASA officially made Webb its top priority, its flagship telescope, as we'll be talking about, its flagship mission, what was called the NGST, its old name prior to being named after Webb, is called the Next Generation Space Telescope. That's why I made a little allusion to it in the intro there. It was known that this was going to be really a leap forward in technology beyond existing space telescopes, which I found out even Hubble, as advanced as it is and was only essentially retrofitted from an existing blueprints for spy satellites that were used during the Cold War, because Cold War ended in 1989, and Hubble was developed in the 70s and 80s. So Webb it really did advance the technology, and it advanced not only it advanced everything about it. The mirrors, the shapes, the actual performance, how they work, how they interpret, how they take in light, how they move, how they're shipped, how the materials interact with the exposure of near zero temperatures of space, and how that juxtaposes with, of course, the raw radiation just blasting it from the sun. It's phenomenal what NASA and in part Canada and Europe was able to help them achieve with Webb. It was already about a decade in the making before NASA decided to, speaking of Apollo, name the telescope James Webb. They named it after James E. Webb, who was the I think second ever NASA administrator, and he was the person who oversaw most of, or at least the first few missions of the Apollo program. He's the one who got it through, talked to Kennedy and Johnson, and he was probably the most important figure other than the presidents in actually getting the Apollo missions successfully completed, getting men to the moon. I think 12 different men walked on the moon, and none of those men died, ever. There was 3 who died in a testing accident, and then beyond that, no one, every mission was successful in bringing those men to and back from the moon. Astounding. So not only was he responsible for landing humans on the moon, a major part of his legacy was also his deliberate efforts to balance out the manned space flights with the first ever robotic missions to planets like Venus and Mars. You tired, buddy? Ernie's tired. He's waiting for me to hang out with him. Yeah, and Webb he paid attention to science just as much as the political aspect of NASA while he was the administrator there. He'd been a manager of an aircraft company, actually, so he was well aware of not only the logistics of how companies and aircrafts are made, but the science and engineering behind all the actual flights and the technologies. So he was able to put a realistic timeline and a realistic momentum behind the success of the Apollo missions. He was one of the main leaders initiating what is still in effect today. It's called the Explorer program of NASA, and it's strictly scientific missions of satellites and Explorer probes out in space that began in the 60s in parallel with the Apollo mission. And just during his tenure alone, it saw a whopping 75 missions launched during 8 years, including missions to Mars, Venus, and Mercury. In 1965, he even suggested that a flagship space-based observatory, then known as the Large Space Telescope, and what became Hubble, should become a major NASA effort. Until then, there was just these kind of minor, secondary, not quite priority telescopes. He didn't create the idea of Hubble or even design it. His hand was in helping it be pushed forward through the political outlets or avenues to get it made, to get it actually funded and produced and sent into space. So his legacy is really an important one for NASA and downstream of that for civilization in general, because he set a precedent for people in high positions at NASA to respect and really prioritize science, pure science, not just science on the side of stealthy military operations and telescopes. And it's, that legacy, that precedent that he set, that affected people like the future administrators and director Robert Williams we talked about, to do to do risky things and explore and really embody what science means. It's to probe the universe, and you can't probe things from a comfortable spot, I thought that was really, really relevant to what Webb, the telescope, is supposed to do, and the legacy of James Webb, and what he did for the American space program. And the priority of the frontiers of science is really what Webb was designed for. It was next generation technology, but it was also next generation actual science, the frontiers of science, where it had been and gone since Hubble and even before then. We have things like dark energy, we have exoplanets, like that I mentioned. These are really significant areas of interest. And they're significant because, not only because we don't know anything about them, and we're recognizing how much further information revealed to us might change our whole paradigm of, how we see the world. But it's just at a fundamental level, it's what fascinates humans the most, is the nature of the grandest scales, and whether or not there's life out there like us. It's really two of the biggest, most profound questions we can ask. What is kind of understated in a lot of the talk about Webb was it's been in the works since the mid-'80s, and it wasn't launched until the end of 2021, was it? That's over 30 years in the making. So it was designed initially. The initial plans for Webb were laid out before Hubble even launched into space. And then by 1995, though, right around when Webb was really getting solidified into what its technologies would be for what specific goals it needed to accomplish, that's when the deep field came out. And then a couple years later, scientists looked at the supernovae and discovered, well, the universe is expanding way quicker than we, at the deepest depths, because within the nearest billion light years or so, you can't really tell what dark energy's doing. But at the deepest depths, dark energy's been working over such vast expanses, over such all the voids between the intercluster voids, interstellar, or the intergalactic medium. The space has been expanding, and on small scales, it's almost imperceptible, but across billions of light years, that makes those distant objects between us and them, or the space between us and the most distant objects, so large and so vast that it's actually starting to be perceptible to significant degrees. And these discoveries in the 90s really shaped what Webb's goals were going to be, and what we're about to discover over the next couple years, and really decades, now that Webb is known to be performing so much better than it was expected to. And to create those and to complete those next generation science goals, as we mentioned, we had to have next generation technologies, and that we're going to go through a list, but a brief look is the shorter the wavelengths, infrared, which is what Webb is kind of tailored to, is longer wavelengths than what Hubble is. Hubble is mostly UV and visible light, much shorter wavelengths, and that's what Hubble's tailored to. That's what they're specifically designed to do most of their primary observations in. And then later on, because the wavelengths are fairly close to each other, infrared, optical, and UV, they were able to attach a infrared instrument onto Hubble, and it's able to get some amazing images. But Webb's primary wavelengths has some optical capabilities, is infrared, and it was specifically precision engineered really adapted to perform exceptionally well in observing and detecting infrared light. Relative to Hubble, though, at wavelengths around 600 nanometers, which is towards the red end of the visible spectrum, Webb's resolution, which is the angular resolution characteristic of telescopes that lets you know how sharp the images they can produce are, is 3 times that of Hubble. So even looking at the same object, Webb is going to be able to detect further objects because they're seeing infrared light that was shifted from visible wavelengths. And so it's radiating initially heavier in the visible and UV, and over time that's been shifted into the more red, infrared, in extreme cases like we talked about, the microwave. But most of it's in the infrared. And even for any given object, Webb is going to perform exceptionally better than Hubble. If we look real quick, we see, just look at this next to each other. The Hubble has a 2.4 meter mirror. Webb's is 6.5. The temperatures they operate at, the Hubble is 21 centigrade. Webb is 200 degrees colder than that. And even the weight, you can see, gives you a clue into how much more advanced the technologies really have gotten over the last couple of years. Webb's almost twice the size and half the weight of Hubble. So the fact that it's 1 million miles further out than Hubble, it's adapted to see the infancy in galaxies, whereas Hubble's just been able to see, the toddler, if we're continuing that analogy there. A deputy project manager at NASA's Goddard Space Flight Center, Paul Geithner, said, quote, "When we first thought of Webb, it wasn't technically possible. We had to succeed at inventing some of the things before we could even learn or begin to build it, which is not unlike the Apollo program in that regard. From lessons learned throughout the decades-long fumbling development of Hubble, which was its own debacle in its own right, NASA had learned a lot of their lessons, that years of planning were needed before the construction of Webb could even begin. And so thanks to precedents actually set by the administrator Webb in the 60s, scientists and engineers were convened in a way in assemblies in conferences, and asked ahead of time what was needed to avoid project delays and major errors, major setbacks. And at a series of conferences, it was agreed that 10 novel technologies, unique innovations, were needed that were known as enabling technologies that had never been invented. They were needed to make Webb feasible at all. And so that's what they did. NASA threw millions of dollars at research and development, and made sure that before they began these huge investments for companies like Northrop Grumman and Ball Aerospace to manufacture the mirror lenses, that the technologies were even feasible to perform. But it was amazing. Over a course of 30 years, with hundreds, actually thousands of total scientists and engineers, they were able to get it done. To understand what drove scientists to spend $10 billion sending a telescope into space,
you must first invent the universe. Thank you very much.
So much of telescopes involve the simple gathering of light and deducing from that information the nature of the universe. And of course, we apply physical experiments done here on Earth and now in satellites in space, and the laws of nature that we've determined from that to this light that we're detecting from billions of light years away. But it really is light at the center of everything. I thought it was interesting to look at the light time it takes for light to travel from certain objects in certain distances across the universe. For instance, it only takes a few billionths of a second for light from this lamp to reach my eye. It takes a seventh of a second for light to travel the same distance as the equivalent to circling the Earth one time. In space, however, that's where light becomes meets its match, and it becomes much less instantaneous, even within our own solar system. And that's, with the different videos I've tried to explain just how vast the distances between objects in the universe really are. We just can't intuit it. It's very hard to understand just how much space is between planets, let alone stars, and then unfathomably beyond that, the space between galaxies. The moon is Earth's closest companion in space, and it still takes light almost 2 seconds to travel from the Earth to the moon. When we look up at the sky, we're only seeing the moon as it was less than 2 seconds ago. And then light from one of the most distant planet, Neptune, takes 4 hours to cross the solar system. The nearest star is over 4 light years away. That's the nearest star to us. So we're only seeing it as it was 4 years ago. It could explode, and we wouldn't know about it for 4 years. That's incredible. I feel like that does help put it in context, because that's the nearest star, and there's billions of stars within our own galaxy. So when you think about it, even within our own galaxy, we're used to thinking of galaxies billions of years away, or seeing them billions of years ago because they're so far away. But even within our own galaxy, we're seeing light. We're not seeing any current light from any star. That's local in galactic terms to us. What we're doing is seeing light as it was 5, 100 years ago, and then 1,000, then 10,000, and then the furthest stars in our own galaxy, we're not seeing until the light from 100,000 years ago has finally reached Earth. And then if we leave the galaxy to our nearest large neighbor, Andromeda, that's 2.5 million light years away. That means light that's hitting us now, emitted when humans were not even a species yet. We had just learned, our ancestors did at least, to harness fire, start chipping stone tools, maybe start hunting and collecting in small villages. It's not really clear what kind of any proto-language we might have had, but we certainly had impressions of thoughts running through our head to be able to have technologies like that and harness fire and cook. I think almost 1 million years ago, we were already cooking things. Then the Virgo cluster of galaxies is our local galaxy group. That's 60 million light years across. That light from the most distant galaxies in our local cluster is emitted from galaxies as they were at the time the dinosaurs were still roaming the Earth. So it's important to know that light dominates our understanding of the universe, and our relationship to it has changed. It's evolved with time, just like the light and the galaxies from which the light we're seeing now have evolved and are still evolving. So I want to explore the relationship between what we know about the universe and what we know about light. I think it's in our DNA to explore the unknown. I think there's ample evidence for it. I think we literally get we get what's called cabin fever if we've been inside too long. We get restless when we don't explore and get subject to stimuli from the world around us. I think learning, like I said, about our fascination with fire and our ancestors' ability to wield fire before we even had language, millions of years before, says a lot about the innate interests that are baked into our DNA. I mean, we have to have a fascination with light and fire, and it's really inevitable that our gaze, given this, would have been drawn up towards the infinite expanse of space, which is illuminated at night, especially in prehistory, by these orbs that are so distant they only look like points pierced through a black veil, draped over the sphere of Earth. Some of them actually would have been bright enough, especially Mars at night, to actually determine, you could see it's some are red, some are blue, and of course that would have correlated to some hues thrown off by the primitive campfires of these early proto-humans. And so you can imagine the connection between space, the stars within space, and these glittering orbs of light just twinkling across the crystalline sphere of the cosmos, and the fires that were so important to the survival of early humans. They weren't just decorating them because of the ambiance, It's fascinating to me that it's an established fact that 2 million years ago, we were already, maybe by 3 million years ago, our ancestors, Homo erectus and whatnot, our Australopithecus had already started dabbling with fire, with maybe walking up to brush fires already going, struck by lightning, started by other means. So it wasn't started by them, but they were starting to use it and starting to play with the effects of it. And over thousands and thousands of years, you can imagine how that would be baked into a cultural, a very important aspect of culture that would have been passed on generation to generation to the tribes that were able to survive by using it in some fashion, whether to ward off predators, whether to fight warring other rival tribes, or just keeping warm during the periodic ice ages that have ebbed and flowed throughout millennia. I think it's easy to make a case that campfire that draws our gaze when we're sitting around it at night, or a fireplace, or wherever it might be, even a simple candle, isn't just purely in our outer cerebral cortex. I think it's baked into our deep, deep psyche, and that fascination made our obsession with astronomy almost inevitable. So as science in the early 20th century was really gaining steam, both in particle physics and the revolutionary explosions in cosmology from Hubble and Einstein, Lemaitre and Friedman, and then Zwicky with the discovery of some mysterious non-luminous substance that is adding 10 to 20 times the amount of gravity to the universe. around and corralling the luminous matter into flat disks of stars in galaxies. All this was working hand in glove. Physicists and cosmologists were working hand in glove to try to reconcile the brand new particle physics with the relativistic gravity. That's a deeper frontier of science that still hasn't been reconciled, called the grand unified theory. We know the atomic forces, electromagnetism, the weak and the strong force, those two forces, they work on the scales of atoms. Electromagnetism works on distances further than that. Gravity works at the largest scales. We think gravitational waves travel outside, disperse at the speed of light, but they work and they don't have any limit to how far that force can interact. So at the origin of the universe, at this 400,000-year-old point that we talked about in the beginning, our observable universe would have only been 80 million light years across. And this 80 million light year in diameter sphere has since expanded into 93 billion light years across. And that 93 billion light years comes from, as we look further back or as we look further in space, we look simultaneously further back in time, because the light we're seeing, it's not that that space hasn't evolved since. It has evolved. It's just that the current light is just now being emitted from 93 billion light years away. The light we're seeing is when it emitted it 13.7 billion years ago. So it's showing us the universe at 93 billion light years away when it was 13.7 billion years old. And as cosmologists and physicists try to reconcile their data and try to understand that as the universe got smaller and smaller and hotter, the conditions were more extreme as time is rewound until the point of the Big Bang. Essentially what we're able to observe as far back as the last surface of last scattering, at which the original hydrogen atoms of the universe emitted their last bit of light before they went dark and cold for 100 million years about, until the first stars formed. This observational evidence is, of course, the truth. Whatever we see, fundamentally, the light that is hitting our lens of the telescopes we're building is the only way for us to know what happened in the past. And it's helping them craft their theories about how physics works at such extreme temperatures, how these forces would have interacted with each other at millions, billions, trillions of degrees, and further beyond that, almost to no end. And it became very apparent to the National Academy of Sciences, the panel of scientists that get together and recommend essentially to the government. They write reports to figure out what the most important science priorities are, and the government takes their recommendations into very serious consideration. In the mid-60s, during and after the continual flood of new data and information coming from these first satellites that were launched into space, the priorities became clear for the National Academy of Sciences. Their astronomical priorities, at least, became clear that the government needs to invest in the wavelengths and sending space telescopes up to observe wavelengths that, of course, the atmosphere blocks from Earth. And this, over decades, over the next 20 years or so, crescendoed into the what's called Great Observatories program. This was the Compton Gamma Ray Observatory, and these all were recommended in the 70s and 80s and built to be launched in the 90s to early 2000s. The Compton Gamma Ray Observatory launched in 91. Actually had a pretty short lifespan, turns out, but then you had the other three were the Chandra X-ray Observatory, launched in the late 90s, I believe, and then Spitzer, launched in 2003. That was in the infrared domain, and actually the predecessor, the official predecessor of James Webb, although we had Herschel since then, so I guess technically maybe the grandfather, pre-predecessor of James Webb. And then the most important of the four great observatories of NASA was Hubble itself, the Hubble telescope, launched in 1990. And although the Compton gamma ray, X-ray, and infrared observatories were really important, and they shed a lot of light on the universe out there, Hubble was by far the most important, and it amazingly still is in operation. I think the Chandra X-ray Observatory is still in operation too. Spitzer was supposed to have some overlap with Hubble or Webb, but shut down into safe mode. It's just quietly orbiting space in 2020, but worked for 17 years, did some great data. And I'll show you a couple images here that you can compare Hubble and or Spitzer and Webb, and just how much more advanced Webb's resolution really is beyond Spitzer's. But it was Hubble that was what's called the flagship telescope for NASA. It was the crown jewel of NASA, and throughout the 90s, since it got its lens fixed, all the way until Webb was launched in 2021. And what Hubble found, like we talked about in the intro, was the limits or lack of limits, maybe, of galaxy formation deep in the universe through its deep field observations. It actually pushed, before Hubble was making its first deep observations in the mid-90s with its new corrected lens, we hadn't seen beyond Z with the redshift of 1. It's called Z, the variable Z is, the letter Z is used as the variable in redshift equations. It goes back to Hubble and his constant about recognizing how fast galaxies are receding by looking at the shift in the spectra, the red shift of the shift towards the red end of the spectrum of absorption lines and distant stars in the distant galaxies. That tells us a lot about the universe, and it turns out that other than the intensity of the light hitting the emitters, the luminosity, redshift is the most important aspect that we can, it's the most important piece of data that we can observe from the most distant galaxies. And before Hubble started making its discoveries and its deep field observations, which, by the way, another instrument that Hubble has is a spectrograph. It's called the GRISM, a spectroscopic instrument. So it too can look at the redshifts of depending on where it sends the light that it collects. It looks at the redshift as well as the luminosity, in typical images that humans can make sense of. The furthest, this is really fascinating, that the furthest redshift before Hubble was only about a redshift of 1, and now Webb, as of early 2023, late 2022, has made redshift observations of over 13. Redshift of 1 corresponds to about, I think, 8 billion years ago, and it's actually an inverse logarithmic non-linear relationship. So because of the expansion of the universe, a redshift of 1 corresponds to, let's go ahead and look at this. There's a paper by not Alex Filipenko, but S.V. Pilipenko. We see here it's just a cheat sheet basically for cosmologists to quickly translate redshift, co-moving distance, and the age of the universe. We could see here a redshift of 1 is equal to, so co-moving is the radius, the radial distance, so not the diameter of the sphere, but the distance between us and whatever object we're measuring. And it's in it's in parsecs here. Yeah, megaparsecs. So a parsec is roughly 3 light years across. So just divide it by 3, or multiply it by 3 to get the light years here. So 3,000 would be 3,000 million parsecs would be 3 billion parsecs, which would be 9 billion light years. And so 1, it's even more. Okay, so it's over. It's give or take, it's 9 billion light years, which corresponds to. They have the redshift on the right side too, so you can make easy lateral movements here. So the equivalent time of a redshift of 1 is 8 billion years old. Let's see. 8, it's a little confusing. 8 billion years ago, which would be the age of the universe, which would be almost 6 billion years old. The furthest we ever looked back in time was 6.5 billion, or looking at objects 6.5 billion light years old, before Hubble observed its first deep field here. And some of the first deep fields that Hubble was able to observe stretched that back all the way from a redshift of 1 to the new frontier of a redshift of 6. So that 6 meant that the universe was closer to 13 billion years old, which corresponded from objects, instead of 6.5 billion light years, it went all the way back to, if we look on our scale here, it went all the way back to 13, so a redshift of 6.5 is going to be less than 1 billion years old, 800 million years old. And now Webb is supposed to go, so far Webb's gone, I think, to 13, I think it's measured all the way here to 13.3. We're going to get into that in the results section. So that's almost having the age of the objects Hubble was able to observe. Hubble's furthest ever observations, and let's see, I think it was 11, a redshift of 11, which corresponds to about 5. Yeah, corresponds to about 500 million years old, maybe 450, 500 million years old. Whereas Webb's redshift, sorry, I was looking at the age down here. The redshift is over here. Webb's redshift has already confirmed. They have candidates all the way to 16, but they've confirmed in just the first few months of getting data a redshift of over 13, almost 13.5. So that's roughly, if we go over here, that's about 350 million years old. So we're looking at galaxies only maybe 100 to 200 years, 200 million years older than the first stars, which is a pretty, it's like It's like only a couple months on cosmic time. It's pretty amazing. Hubble really just, it looked 5 billion years further into the past. And what this corresponds to, let's see, redshift of 6 corresponds to about about 27 billion light years away, with expanding space, remember. And until Hubble got its infrared, near-infrared camera installed, it actually didn't even detect some of the oldest, but once it did, that's when it was able to detect the 11.1, and of course Webb launched in late December, so basically early 2022, late December of 2021, did about 6 months of, or at least a few months of just calibrations, getting warmed up, and so it's had about 6 to 8 months of time to actually collect hard data. And in just this half a year, 6 months or so of data, Webb has already pushed bound way past that, and there's potential galaxy candidates all the way at redshift of 16. That was just came out of just the first couple images that Webb observed, and so we're going to have deep fields from Webb over the next couple of years, definitely 2023. So maybe even by the time some of you guys are observing this, it's gonna be, this is gonna be old news. The more, just like a regular camera, the more you hold the lens open, the shutter open, and collect light and photons, the fainter objects you're able to see. And so we're gonna have these exposures, not just of 12 hours, like Webb's first deep field of J0723, but we're going to have exposures of hundreds, a combined hundreds of hours in the future. And so I'm really looking forward to that. Redshift of 16 is the current kind of candidate. So it's not confirmed, but it's likely it might actually be looking at galaxies that are between 200 and 300, so about 250 million years old, which is only about 100 million years after what currently cosmologists think is the beginning of cosmic dawn, the first nuclear fusion from condensing matter in the universe. And so Hubble's first deep field was in the mid to late 90s, and then of course once they discovered how many galaxies were in there, they had a bunch of follow-up deep fields, because that became priority, and they realized how much data was actually there. And an astronomer said, one of the most striking things about the timeline of galaxy evolution visible in the original deep field photo was that there was no beginning in sight. Even the ultra deep field taken 20 years later, still it went redshift 6 to almost a redshift of 11, and it shows no end of galaxy formation. So one of Webb's goals is really to see so far back in time that we will finally start to see a thinning out of galaxies. But as of now, there's just an endless field of galaxies, no matter how far back in time we go. And that was one of Webb's primary goals. The National Academy of Sciences, they released their decadal survey, in what became the decadal survey, the initial one in the 60s, then for every decade ever since. The 60s and 70s one recommended, hey, let's put all our resources towards Hubble, this large telescope later on named Hubble. And in the 80s and 90s decadal surveys, that's when Webb's first conceptions was proposed. And by the year 2000, the 2000 decadal survey said, hey, government, Congress, let's go ahead and we've seen what Hubble can do. We've seen the deep fields that Hubble has been astounding us with and pushing the frontiers of observations with. Now let's build a telescope even more adapted to IR, so we can see even fainter galaxies, and let's make the mirror 3 times larger, 6 to 7 times the surface area. And let's throw it 1,000,000 miles further out into space. And we're going to do it, by the way, in that survey, they said that we're also going to be able to do it in less than $1 billion for a cost of maybe $500 million to $1 billion, which is laughable because one of the reasons Webb almost got canceled multiple times was because it ended up costing over $10 billion. I think 11 billion was the final number. But adjusted for inflation, Hubble actually cost about the same, because it was built in the 80s. So if you just, I think in $1990, at the time it was launched in 90, it was $5 billion was the price, and it was meant to be built for only 500 million or something like that. So Hubble had the exact same series of oversights and over budget obstacles and stumbling blocks, but it ultimately was worth it, really. And I saw one estimate was that the cost of one aircraft carrier, and the U.S. has, is it 5 or 10? Anyways, let's just say 7. There's 7 total aircraft carriers, and each one is about the same as the cost of Hubble or Webb, $10 billion. So, when you think about it, I think at one point we were spending $1 billion a day in Iraq. I don't know how much we're spending now overseas on the military, but so if you took a week's worth of expenses and put it towards another telescope, we'd have 2 Webbs out there. And we'll talk about it later, but they actually are coming up with that already in the works. Webb, of course, took since the 90s to be built, and we think by roughly the year 2035, maybe 2040, we'll have another version of Webb with even more hexagonal mirror segments unfold out in space, and this one is actually going to be the direct successor to Hubble. And this new one called LUVOIR, standing for the large, I think it's large, but the UVOR part is UV optical infrared. So it's going to be covering the whole range that Hubble does, but it looks pretty expansive. I'll maybe pop a picture up right here if we don't get to talk about it later, but I'll definitely be talking about it more in the future. Seems amazing. And I'm lingering on this deep field because was one of the what's called science drivers. I forget if I mentioned this before, but a science driver is basically a science goal that a telescope or other instrument has, that it's built to pursue. And there's 4 main science drivers, but really they can be encased in the umbrella of 2 main science categories. And one is the early universe, and doing deep fields like this and trying to understand more about the evolution of the universe and what the true distance is. We have a current model called the lambda cold dark matter model, and we'll be talking about what that means in just a bit. But Webb was actually built to try to break that model. It was built literally to see if the predictions stemming from particle physics that predicted the cosmic microwave background, and we have theories, of course we can't go back in time, but we have an understanding of particle physics to a certain degree, to actually a really high degree, based on experiments here on Earth with our particle accelerators. So we understand, we meaning physicists, very much unlike me, understand some great degree of how the early universe would have evolved. They then use other characteristics of the universe, like dark matter, to run simulations, insert it into their equations, and predict what exactly is going on as far as what dynamics across the universe are leading to galaxies like our own, and ultimately to life, which is the second umbrella science driver category that Webb was specifically built to help shed more light on, which is exoplanetary observations. So the two main goals of Webb were to push or break the frontiers of the deepest understanding of cosmology and find exoplanets on which alien life could possibly exist. The current cosmological model of the universe is called the Lambda. It's called the Lambda LCDM model, the Lambda Cold Dark Matter Big Bang model. And the cold part of the dark matter indicates that the dark matter doesn't interact with regular normal matter, or the radiation, the light coming off of normal matter as well. So it's definitely a dark foreign substance that we haven't detected yet. And particle accelerators on Earth are really one of the huge hopes, is that one of these days we'll be able to detect some signs of it in a lab. Spitzer was, after Hubble, the second most probably important telescope, or at least in terms of major discoveries on the broadest scales of the universe. Hubble started operating, making a lot of its discoveries in the mid to late 90s. Spitzer was about a decade later, in the early 2000s, for 10 or 15 years. And Spitzer actually discovered that TRAPPIST system that Hubble, or Webb, recently had a team of scientists telling it to look at and explore even further. We'll talk about that a little more in the results section. Spitzer, often jointly with Hubble, was able to see the universe evolving far back in time. And Hubble had a larger lens. Spitzer was a much smaller mirror, so it wasn't able to resolve a lot of these objects and put up a lot of comparisons. You'll see Spitzer will only have objects look like pixels, extremely low resolution. And Webb, looking at the same object, it looks like a high def, or at least 720p, like when your internet's kind of bad on YouTube, version of it. So it's way, way sharper. And because Webb is in the same category as Spitzer, looking at infrared, very specialized to look at infrared. Spitzer was, even though it had lower resolution than Hubble, Spitzer was able to detect objects much fainter, and even completely outside of the ability of Hubble to detect them at all. But for Spitzer, they would just detect, red, orange blobs, or at least blobs that we color-coded to look red and orange on our screens. But it would detect luminosities that Hubble didn't even have the detectors to see, all the way back to about 3% of the universe's current age. Spitzer found galaxies with redshifts greater than 6 that emitted no optical light whatsoever. So their optical light had completely extinguished and shifted all the way into the infrared. And in 2005, an amazing result that Webb should be able to really follow up on here is that John Mather, and this guy, I feel like I haven't given him a proper introduction yet. He was the chief scientist in charge of James Webb being built and developed, and he was, he was the head of all the actual science and engineering that was going on behind it, and he helped define the science drivers for Webb, and he also had an important hand in a ton of other NASA endeavors, including COBE and WMAP, the famous satellites mapping the cosmic microwave background. So Mather reported that one of Spitzer's earliest images may have actually captured the light of the first stars in the universe. So John Mather, Dr. John Mather, he specializes in early universe cosmology. An image of a quasar in the Draco constellation. intended only to calibrate the telescope, was found to contain an infrared glow after the light of the known objects, the known stars, galaxies, in the picture was removed. Kulinski and Mather are convinced that the numerous blobs in this glow are the light of stars that formed as early as 100 million years after the Big Bang, redshifted by cosmic expansion. So it's for this reason that the James Webb is primarily an infrared instrument. In 1980, the Marshall Space Flight Center, NASA's center responsible for creating Hubble, studied the possibility of launching an 8-meter, 24-foot telescope in the external tank of the newly minted Space Shuttle. 2 years later, the third ever decadal survey was released mentioning the priorities of the coming decade. And this put an emphasis on IR and infrared. The report made a point to say most radiation in the universe is ultraviolet, optical, and infrared emitted from stars. So in 1985, discussions of a Hubble follow-up was already started in the 1980s, even before it had launched. After the 81 decadal survey infrared recommendation, they realized, hey, Hubble took a long time to get actually made. We need to get the ball rolling on this. And the deputy director of the Space Telescope Science Institute, Garth Illingworth, he was asked to start thinking of what we need to do. Like, what's the most important? What's the largest project we can get going? Now that Hubble is the flagship mission we dumped all our money into, NASA, the NASA funding, the politicians in charge, specifically of the committees that allocate funding to NASA, they're going to be looking to say, hey, what's the next project we need to start gathering resources for? In 1986, as far back as that, they were proposing a telescope specifically to look for exoplanets 10 years before the first one was found. So they had a 1989 feasibility study, and they had a major workshop. They had a 3-day meeting among 130 astronomers and engineers. There are 2 nominal concepts, the 10-meter telescope in space in high Earth orbit and a 16-meter telescope on the moon. It's a 45-foot, over almost 50-foot telescope on the moon. And here's some designs, some preliminary designs. Interestingly, we had what would become Webb have this this baffle around it, but it didn't quite, I don't know if it had the segmented optics, the hexagonal mirrors, but the one on the moon clearly did. So even back then there were already designs, and I think this came out of Northrop Grumman's military experience building military satellites for the U.S. These were prototypes that they had already mocked up, but in 89, you could see this one on the moon looks exactly like James Webb. It's fascinating. A little artist concept there. Here's one of a 16-meter moon telescope. An ultraviolet visible in IR or UVOR ring telescope, and you can see the people down there, the little guys. Just how big that telescope would be. Good Lord. And what's amazing is that they're building one even larger than that on Earth. Okay, so I guess that initial design, it was just too low resolution to see, but it actually was segmented optics inside the baffle there, the shield. But so they've had the idea of segmented optics for a while. And this is the course design. Spherical primary telescope with 3-mirror corrector. Cassegrain. That would evolve into the course design that Webb ultimately used. Let's see. Here's some. Here's what they they were trying to figure out how to fold it up to put it in, they had to fold up Webb and put it in the rocket, the Ariane 5 rocket down in South America there. And they had a couple different ideas for how to do it. Like either it could fold up overlapping like a flower petal. It could do what it does, which is just have wings that fold back. And then each individual mirror has its own series of motors that is connected to the back of it. That's actually helps like align it to perfection. And then they had one design where it was like a mock-ups was to have it literally like a record player, where it would extract, like the mirror segments would be stowed away, and then one by one they would have an arm grab it and put it in place like a record, an automatic record player, grabbing like a jukebox, I guess, grabbing records and putting them in place. Here's an early prototype of segmented optics right there. I guess with half the hexagons sawed off to make it into a circular shape. And then here, that's pretty close to the actual final design. But the 1991 decadal survey, 10 years later, or a year after this workshop, but 10 years after the initial kind of impulse to start really seriously looking into infrared. Yeah, this 91 decadal survey had a great prediction of discovery. So even in the universe we can observe, they say here in the survey, even in the universe we can observe many fundamental surprises surely await us. It's likely that major properties of the universe are yet unknown. The expansion of the universe was unknown in 1920, and the existence of quasars, completely unsuspected in 1960. Who can imagine what astronomers will find by the year 2000? This was before dark energy, by the way. And then 5 years later, there was a second major feasibility study. This was the second of 3 big steps towards making Webb come to reality. This was the 1996 Hubble HST, Hubble Space Telescope and Beyond Committee, it was called. And this committee was convened because in 1996, Hubble had finally fixed its flaws in the mirror, and these images like the deep field and other images were just blowing away any previous imagery of the same objects in astronomy. And so this was saying, okay, we nearly flubbed the Hubble, which was it was like a $500 million mistake, basically, by the time you calculated all the wasted time that Hubble was sitting there kind of uselessly orbiting Earth, not able to really take clear images, and then sending up a shuttle and making the corrective instruments that would fix the lens aberration. Essentially what happened was they ground the mirror, they polished it perfectly, but they polished it to the wrong curvature. So towards the outer edge, I think it was a little bit flatter than it was designed, its specifications indicated. And it turns out what happened was they used the same machine to measure, they used the same machine that they used to polish and shape the curvature to measure to see if it was the right curvature. So I guess there was a flaw, or there was a wrong, incorrectly calibrated metric in that machine that just translated into the measuring, the testing. When they measured it for accuracy, it showed that it was fine because the calibration in the actual machine was just wrong. And so it screwed up Hubble, and it made all the pictures blurry for the first couple years. And this was a huge debacle. And Jay and Webb, they ended up specifically testing it with third-party instruments so that they could be sure 100% that this wouldn't happen again. Dr. Mather, John Mather, we talked about before, this is when he got on board was right after the 1996 feasibility study, which said basically, hey, Webb or Hubble's fixed now. Sorry, I know I keep going back and forth. Hubble is now fixed and it's doing remarkable science. And this study said that we want to lean into these capabilities of Hubble, and we want to push them even further. I mean, we're just 30 years in the making. We're just doing the first couple years of real science with Hubble, and now we're already looking down the road for the next great telescope and to push whatever Hubble will and has discovered even further. And Mather got on board at this point. He said, quote, "I got goosebumps when I read what HST and Beyond Committee outlined was possible in astronomy." They really get philosophical in a lot of these reports. They add the philosophy and the inspiration to humanity that these add, which inspired my intro about the Apollo missions and science fiction, inspiring entire generations of people to get into the STEM fields and try to explore our world through science and mathematics, and the hope and the expectation of new surprises and new, deeper understanding of the universe that gives us. The main case that this report made, whose fundamental goal was to encourage the funding of the James Webb Space Telescope. The main point that they tried to instill in the report was that, hey, Hubble almost got canned because it was over budget, running way behind schedule. Even though the Challenger disaster happened in the 80s, Hubble was supposed to launch in the early 80s. Challenger disaster happened, the space shuttle blew up, and the whole shuttle fleet was landed for a couple years. And even then, in 1990, Hubble just barely was ready. The team had barely completed the, appropriate checks for it. And even then, Hubble was found to be screwed up with its lens. So it was almost one disaster after another. It was almost going to be this orbiting reminder. If we hadn't fixed the Hubble lens, it would have been this orbiting reminder of failure, the failure of NASA, but also the failure of the U.S. And on the worldwide stage. Undoubtedly, that was the angle that NASA administrators were pushing the politicians on. They were saying, hey, we don't want to look like a failure. We don't want to have this $10 billion, $5 billion at the time in the 90s, museum piece. We want to actually do some real science, do what this thing was built to do. So they did. It got fixed. It produced remarkable images of nearby stuff, and then stuff like the deep field. And there's actually, upon close scrutiny of the value of space telescopes after Hubble's near failure, what it actually told us was there's a case for an increase in NASA's budget, not a decrease, even though there was some ineptitude with just how close Hubble came to just being a disaster, and especially a PR disaster on the worldwide stage for the U.S. There's actually a case here based on the extraordinary performance of Hubble for the increase in NASA's funding. And not only general funding, but funding for other major missions like this. A major theme of the report is the philosophical justification for the quest to understand the origins and the evolution of galaxies and the identification of terrestrial exoplanets. Quote, the great frontiers of modern science. Yeah, this report was really important for me making this video here, because it highlighted again and again the value of inspiring the public through the research. It wasn't just to develop military technologies to maintain our dominance on the world stage. It was to encourage the civilians and the youth to, just be better people, to have meaning in their lives, to have a purpose, and that purpose was to solve these magnificent problems that the universe presents us with. Lyman Spitzer, he said in 1946, space telescopes won't just supplement our terrestrial science. They're not just going to, again, he was outside the box. He wasn't complacent. He wasn't saying, we just need to fill in some gaps in our knowledge. He's saying, no, they might just modify profoundly our basic concepts of space and time. And he was right. The report says there's a social contract between science and its patrons, the public. Because remember, NASA is a government institution. Astronomy's real contribution, it says, is its remarkable appeal owed to the resonance with a basic and eternal human preoccupation, which is to look in the sky and ask, what is this? And further to seek to know, what is my relation to this? It's in humans' nature to be curious, and astronomy nourishes that curiosity. Our society calls for a reinvigoration of respect for learning and a love of knowledge. Astronomy has a vital role to play in introducing young people to the intellectual and spiritual rewards of science. And there's one great quote I posted on my Instagram from Carl Sagan that said, maybe I can find it here. The very act of understanding is a celebration of joining, merging, even if only on a very modest scale, with the magnificence of the cosmos. Science is not only compatible with spirituality, it's a profound source of spirituality. I just love that one so much. And this report even identifies the Carl Sagan's Cosmos TV series as one of the most impactful educational outreaches that there's ever existed. It goes on a little, more philosophy. The quest. We found two themes overall that have broad appeal to the public. That's the quest for the exotic and the quest for our place and origins. We want to know, we want to go into the unknown, explore, expand our understanding, and at the same time, use that understanding to understand more about ourselves and where we've come from, where our ancestry originates from, including all the way back through biology and the physics of the universe. We want to know, what is this universe we're a part of? What is its fundamental nature? What's going on? Where's it going? What other forces are at play within it? It's just so cool that to see a scientific report actually incorporate these profound philosophical concepts. I personally just really get a thrill out of seeing writings like this. And it says, here's what we need. It says, basically all the things. It needs to be infrared, needs to be large, be able to see beyond redshift of 10. And it says for a cost well below $1 billion, and possibly as low as 500 million. So I can't help but think that was inserted for the any of the politicians reading to help get that passed. And Webb became the focus of the 2001 decadal survey. It was the top recommendation, which was to dramatically increase the capability of UVOR observations with the next generation space telescope, and also the giant segmented mirror telescope on the ground, which is becoming the extremely large telescope, the one that was, I think it's being built in Chile, and it's going to be like 150 feet across. I'm going to have to do another video on that because that is extraordinary in its own right. And this 2001 report, it mentioned, again, just American society has always been attached to exploring new frontiers, and in the deep human desire to understand how we came to be, whether we're alone, what the ultimate fate of the universe is. And where'd the part where Carl Sagan was? Yeah, there we go. They said that Carl Sagan's Cosmos, this guy, was the most successful experiment ever in public science education. It's had an audience of 400 million television viewers in about 60 countries. In the book, the one I just held up, from 1983, is the best-selling English language science book in history. And they emphasize in the report that Webb and its data, and that's actually an aspect of the data being released, and that's actually why NASA has quite a large marketing budget, or at least they make a point, they at least emphasize that all the NASA and ESA images I use here are free to use with attribution in the description at the end of the video, precisely because of the philosophy that's in these reports that are written by people working with and for NASA, and they're writing to and for the government. They're saying there's an almost ethical, well, no, it's not almost, it is an ethical duty to convey the knowledge of our universe to the public. It says astronomers have a vital role to play in contributing to the development of science education in the United States. Among scientists, it's well aware here that astronomers make a disproportionately large contribution to the improvement of public science literacy, relative to the comparatively small size of the astronomical community. And that's because of the broad appeal of astronomical concepts and ideas. This, of course, remember, this is the National Academy of Science Astronomy Division here. Professional astronomers and cosmologists is their recommendation. This is their recommendation for where funding for that decade to NASA and the Space Telescope Science Institute will, what projects that funding will go towards. And once this report came out, Webb hit the ground running. The overall basic design of the instrument had been conceptualized, but the specifics still needed to be worked out. And there was a ton of formidable challenges, including the extremely low temperatures, because so much infrared light is emitted from objects within a couple hundred degrees of our ambient temperature at room temperature, is just tons of radiations flooding, and it drowns out any potential detectable radiation, infrared radiation from the cosmos. So it has to be super cooled down to less than 50 degrees Kelvin. The further in the infrared you go, the colder it has to be. And they were previously just set in these big thermoses with huge insulated walls and super cooled down with nitrogen, and that only lasted for so long. James Webb is different. They essentially designed it to be exposed to the cold of space, because remember, it's behind this huge tennis court size sun shield. So the fact that it's in this sun shield is 5 layers separated, and it's very reflective, so it reflects a lot of the sunlight back. It lets basically no light at all reach the instruments sitting on the other side of it. It's one thing to have a sun shield, but it's another to have this 70-foot long, 40-foot wide, 5-layer thick, 5 separate distinct layers that have to be separated from each other with space in between, so that the heat absorbed by each layer successively can dissipate away into the cold space between the layers. And so each layer, as it approaches the spacecraft, it gets closer and closer to the spacecraft, it gets cooler and cooler and cooler. It insulates less and less and less. It absorbs less, increasingly less heat. These things were extremely sophisticated, elaborate systems with hundreds of moving parts to them to be able to tuck into small space and wrap around the spacecraft so that the telescope could fit in the cone head, the head cone of the fairing, it's called, of a Ariane 5 rocket, and deploy once it got launched into space. And of course not get hung up on itself. And the important thing to remember with Webb, it must have been pretty nerve-wracking for anybody working on it, spending any significant chunk of their life working on this thing, was that this was distinct from Hubble, in that Hubble was in low Earth orbit, meaning the shuttles at the time, before the shuttles got permanently grounded after 2011, the shuttle missions as a whole came to an end. They could be repaired, and the Hubble was actually meant to be accessible by astronauts, so astronauts could go up there and literally turn bolts and fix and add things to it. Webb, it is completely inaccessible to humans. It's a one-shot deal here. So that means anything that could go wrong, they were praying Murphy's Law wasn't right. Anything that could happen, and anything that did happen, anything that went wrong at all, was completely irreparable. They could not go and fix it once it was launched. It was just a one-way journey to 1 million miles out in space. And that must have been really nerve-wracking. And given the hundreds of parts, moving parts, to deploy the sun shield, not to mention the fine-tuning, the thousands and thousands of cables and motors and mechanisms, servos, and on the just spacecraft as a whole. This has to be perfectly engineered. There is no room for failure, no wiggle room, no tolerance for some minor mistake, because if something would have happened, then it would have been a $10 billion, 30-year, at least 20-year mistake. It would have just been a pure catastrophe. And in the first couple of years, it seemed to be going pretty smooth, but yeah, there was a lot of times that throughout the next 10 years here, from 2000 to 2011, when they were way over budget, had to cut back a lot. They even fired some people, some lead manager, director people. So it was seriously on the line multiple times. It was this close to not being made. At one point in the 1980s, a few scientists were actually being very realistic, especially in the light of the current Hubble debacle. They were saying, well, Hubble's essentially costing $10 billion. Again, that's adjusted for inflation. So they're saying, hey, it cost, this much money. This is probably what this new telescope's going to cost too. So, adjusting for inflation, they were right in estimating in the 80s that, yeah, it's going to cost what in 2015 will be $10 billion. And instead they, of course, submitted officially in the official documents to Congress to look at, to get Webb off the ground, the numbers of the much more politically appealing 500 million to $1 billion at max, and then at one point there's a congresswoman who named Senator Mikulski. The archives that all of Webb's data go to, so that scientists can look at, because remember, there's just gigabytes of data for every little picture we see. There's tons and tons of data behind that. The archives ended up being named after her namesake. And the directors in around 2008, during the financial collapse, the director in charge of Webb came under real close scrutiny. He had to go in front of Congress and say, explain, why are you billions of dollars over budget? And Mikulski demanded an independent review of the program. And these other managers, scientists, economists, engineers from outside the program came in and said, hey, okay, you guys are screwing up. You guys are making these unrealistic timelines. You're, just way behind. You're not making realistic predictions about how long it's going to take to make and manufacture these materials, the mirrors, the instruments. You're not being realistic about how much it costs to run the facilities and employees to develop this. There were a lot of cutting edge technological developments with these enabling technologies they were developing, and just everything came into a perfect storm, or near perfect storm, to wipe out Webb during the 2008 collapse, because Congress and the general budget of the country after the housing market collapse was one of the few times the left and the right were unified against government there. Back in 2008, there's the Occupy movement from the left and the Tea Party movement from the right. All their other politics that distinguished them aside, they were both very much against big government spending. And they scrutinized government. And of course, this was all during the time of Webb being way over budget. And they're saying, hey, why are we spending money on this? So they began the project in the early 2000s with a 2007 launch date, and that got pushed back to 2010, 2011, 2014, 2015. Every year they would go up to before Congress and say, hey, we don't have enough money. We need another 100 million, another 300 million. There was an actual proposal to cancel the project that went before the floor, and this Senator Mikulski, she was the one who fought for it to keep going, but she made a point to say, hey, listen, you guys need to come before Congress and tell us what you're doing to correct this. The sun shield was, of course, huge. There was one point where they thought they had everything figured out, and then there was these little pins to keep them retracted or keep them folded up, and then it would, when the pins retract, it was holding the sun shield in place in its folded configuration. And when the pins came out to let the sun shield unfurl, they found that, luckily, it was like just a very lucky find, that light at certain orientations from the sun, if it would have been like this and not went unnoticed, would have hit the instruments going through in some precise configurations. Light would have perfectly aligned with all 5 pinholes, and so they had to go back and that would have destroyed the instruments if it got hit with direct sunlight, even from a tiny pinhole beam of light. It would have been raw, exposed sunlight radiation on these delicate infrared instruments. And so they had to go back and adjust the pinhole placement so that they were offset from one another, so no matter from what angle and orientation, no sunlight could ever reach through all 5 layers and hit the instruments. So that was just one of many, many examples that they ran into. The sun shield even, they made it such a delicate process. It took days to unfold. They wanted it to go super slow, not be rushed, not get snagged. It was a very meticulous process. So from 2011 to 2021, there was more postponements and rigorous testing. They were tested in this actually the same vacuum chamber, these massive vacuum chambers that were used for the Apollo testing and R&D for vacuum testing equipment and spacesuits and whatnot. In, I believe, Austin, Texas, or somewhere in Texas, and at the Johnson Space Center. Chamber A, cryo test. So they would put them in these vacuum chambers, put them separate, and then together they would test the fully developed, assembled telescope. In 2015, the ISIM, the Integrated Science Instrument Module, was tested with all 4 science instruments for 3 straight months in a vacuum chamber to make sure the instruments worked as expected when deployed in space. So there was cryo testing, testing at temperatures that are, just unimaginably cold. Like, we cannot imagine. It's something like negative 250 degrees centigrade Celsius. It's way beyond cold. And just to think of like the way things shrink and expand in different temperatures, the fact that they were able to test, to not only build the telescope mirrors in particular, everything else of course would shrink and all that, but the mirrors had to be so smooth and so precise and at just the right shape, as we figured out with the Hubble telescope being at the wrong curvature. And they have to be, first of all, they have to be as polished, as smooth enough to, I read in one article, they have to be so polished, within the fraction of a wavelength of the light that they're observing. And at infrared wavelengths, that's nanometers of thickness. They can't have any aberration on the lens surface, the mirror surface, more than a couple nanometers. And the analogy of that, and this blew my mind when I read it, was that if you blew the entire telescope up to the size of the United States, if one of the mirror segments was the size of Texas, it wouldn't have an aberration larger than your ankle, going up to your ankle, the height of your ankle. That's just astounding. Like, that's unimaginable how smooth that really is. And then on top of that, they have to make these not only so that they don't drastically shrink, or what they actually did was make them so that they shrink into the perfect size. But they have to be able to make them so that they shrink into the perfect size in the chamber for 3 months, come out of the chamber, and expand again into ambient temperatures, and then are able to re-shrink back in space once it gets launched, with no room for error. Again, this is a all or nothing mission. And so not only do they cryo test them, they vibrate test them rigorously. And at one point, I think late in the development, they were doing a vibration test, and they blast them with sound waves. They physically vibrate the machine. They hook it up, the telescope. They bolt it down to a machine that vibrates to simulate the rocket, the acoustic vibrations of the rocket launch itself, and that it's going to have to withstand. And at the end of the test, in this vibration testing, there had been nuts and bolts that were on the floor that had, at one point, they didn't know where they came from. They just knew it was generally from like the sun shield area. So there was lots of kinks that were ironed out in testing. But the technology is astounding to think of that not only do they have it that precisely polished, these mirrors and all the materials involved really, but the mirrors in particular are the most impressive, I think. They have these beryllium mirrors that are polished and then sprayed with it's gold that's been made into, basically gas, because it's such a thin layer. It's like on the scale of nanometers, a thick layer of gold on the mirrors. So back in the early 2000s, to create these enabling technologies, they pumped in about $50 million into the R&D of it. It was half the weight, of course, because, it had such a big mirror that if it had the same technology used as Hubble for the mirror, it would have been some ungodly number, which the rocket simply can't lift that much. So they had to use this lightweight means of constructing the beryllium mirrors so that they actually bored out honeycomb patterns in the back of it to, literally just etch out extra weight from it, but maintain a rigid structure behind it, because that can't flex at all. Remember, this when you're talking about restrictions on the order of nanometers, you can't have any flexing of the frame on which the mirrors sit. And then the spacecraft itself was made out of lightweight carbon composite material, capable of maintaining its rigid shape to 1 in 10,000th of a human hair. That's insane. At temperatures near absolute zero, still while maintaining exceptional load-bearing capacity with, minimal thermal expansion. So some of these technologies, they were near and mid-infrared detectors, the sun shield materials, the micro shutters. This is something super cool. We'll see this picture here. You can see these. This is an array of these literally micro. This whole array here is the size of a postage stamp. Each shutter is about 100 by 200 microns. That's a millionth of a meter, about the width of 3 to 6 human hairs. In each of these tiny shutters, they can be opened with a magnetic force that's added to the back of them and precisely chosen. So based on where stars are, if you want to block out stars, you allow light from only certain shutters. Or if you want to measure a star and then not get any surrounding light contaminating that measurement or the observation, you only open those shutters that line up directly with that star. And there's 62,000 shutters on this one postage stamp sized array. And there's going to be 4 of these. God. And then the advanced actual digital programming and technology behind the wavefront sensing control. It uses a set of complex mathematical algorithms and software programs that help determine the best position for each of the telescope's mirrors, and it adjusts their position automatically if necessary. So even if they go out of alignment, they have these actuator motors attached to the back of each mirror segment. They have 6 of them or 7, and it literally flexes and moves the whole mirror. It can flex individual points of hexagonal, one of the 6 points of each hexagon, one of the vertices, or it can move the whole mirror to allow all 18 to act together, each individually being adjusted in unison as one single monolithic mirror. So we've finally arrived at the completed telescope. Here we can see it's being maneuvered inside the facility. It's a 21-foot telescope wide, and for anybody listening to this, I'd highly recommend checking out some visuals on NASA or YouTube about the actual telescope. It's so massive. And then we can see the boom arms here. Those extend out to 3 arms. That one's folded up. So remember, this is all designed so that it can be, the whole reason it has hexagonal mirror segments are so they can fold up inside the rocket. And you can see, actually, it's funny. One thing I actually didn't notice until just now. They actually had to blur out the actuators right here because these were some of these enabling technologies. That's funny. I never noticed that. The actuators are insane. We'll talk about that in a minute, but they basically flex each individual mirror. I think I mentioned there's about 6 or 7 on the back of each mirror, and they work to get the clearest picture possible so that all 18 segments are lined up to the same point. I'll start this video here. We can see the path of light, the the way light is directed, and it has 4 mirrors. So it's the 21-foot mirror. It's got a square footage of 200 and something, 250 square feet. It's about 7 times more square footage than Hubble has. And it bounces off that primary mirror. It then gets reflected off this secondary mirror, which itself has actuators. It has its own small little motors in there that are able to adjust that. And then it goes into the center of the primary mirror, where 2 more, the third and the fourth, tertiary and the quaternary, maybe, telescope mirrors are. And this third one here, the tertiary, the one it's bouncing off of right there, is the only static mirror in the whole system. So you can see the light hits a focal point and then goes beyond it and then gets bounced off this convex. It's a hyperbolic convex, so it makes a really... the images, one after another, they're being flipped and distorted until ultimately, after they bounce off this static one, which the fourth one and then the primary and the secondary are all being adjusted to be able to, of course, make the most precise high-resolution picture possible, being sent to the back of the telescope elements, the instruments in the back, beyond, inside the guts, inside the heart of the telescope. So it once, by the time that light has reached all the way in the back of the instruments, and the image has been adjusted by 3 different mirrors to make it super precise and to make it as accurate down to the level of nanometers. So we talked about how they were smoothed so that if each of these large hexagonal segments here were the size of Texas, there wouldn't be a bump on them, an aberration higher than your ankle, higher than a human ankle, if they're the size of Texas. Just think about that. That's phenomenal. And these little blurred actuators, this proprietary government technology here, they then further adjusted that perfectly smooth lens, because it is bound to be subject to some distortions through the temperature change as it goes from room ambient Earth atmospheric temperature through maybe even getting a little heated up inside the fairing, the nose cone of the Ariane 5 rocket as it's being launched and piercing the atmosphere. And then once it gets into space, of course, it cools down rapidly. So they purposely made it in an incorrect way, perfectly incorrect, so that it would cool down. It would cool down and shrink into the perfect shape, curvature it needed to be, with minimal warping. And any excess warping they would fix with flexing by adjusting these actuators to such a fine degree. This is why they had to blur the pictures out here, because they're so advanced. They adjust it to I think it's within 15 nanometers. But the 4 mirrors create what I mentioned earlier. The 4 mirrors adjust the light. They manipulate the light that's falling on them and reflecting throughout the 4 mirror system to make an effective 431-foot focal length. It's called that coarse design there. Make where did I put it here? Make the focal ratio something like a I don't know what you call it. I'm not a camera connoisseur, but photographer. Maybe they're also called photographers. It's a 1/20 focal ratio. It's pretty large. It's 21 feet wide, and they're able to get an effective focal ratio, a 1/20 focal ratio, to get a focal length of 131.4 meters, which is 431 feet. It's incredible. The point is to see faint objects really far away. And so the redshift we've been talking about, mentioning, is intended to reach redshift of 20, z equals 20, probably 25, and possibly even a redshift of 30, which would be around 100 million years, which would be, as far as our current understanding, that would be before the first galaxies even formed. These dwarf galaxies consisting of massive metallic or non-metallic massive stars out of like mostly hydrogen, pretty much entirely hydrogen, and just maybe a small amount of helium too. Whereas stars today, it's kind of reverse from what you would think. The way they name them is the most recent stars are actually the third generation of stars, but they call them population 1. Further back in time, it's population 2, and then they think the first stars are actually called population 3, and that would be the first generation of stars. It's probably some historical reason how they used to label types of stars back, in the 1800s, I'm sure, for that reasoning. But the goal is, to see population 3 stars. So the light comes in, bounces off the primary mirror, hits the secondary mirror, both of which have 5 or 15 nanometers actuators on them. They send them to the center of the primary mirror, where the third and fourth mirrors are hiding. They're getting smaller and smaller, but they're both polished to within 25 nanometers of smoothness. And the third mirror, the tertiary mirror, it removes any resulting astigmatism, and also flattens the focal plane. Then the fourth flat mirror, called the fine steering mirror, is used for pointing and stabilization, and very small offset maneuvers as well. So between 4 orders of reflection, 3 separate systems of fine steering, the light can be literally to within nanometers guided into the instruments. So if we go back there, you could see the guts right there. Yeah. I believe that might be it right there. So that's the housing that they're putting the scientific instruments in, and on one side is the mirror, and the other side is the sun shield there. And you can see, look, they have to wrap their sleeves to their gloves to prevent any contamination. The gold aspect, I just wanted to talk about real quick because it was actually really super interesting. Why does gold reflect red and infrared radiation so well? And there's a graph, I'll try to find it to put here, that shows you that silver reflects essentially all of the visible spectrum. Gold reflects well above 90% of 600 nanometer light, orange-ish light, and falls off to only around 30 to 40% at 400 nanometers. So even though they could have maybe, if it wasn't gold, they could have, if it was like a traditional looking silver mirror, they might have been able to attach some green and blue filters even onto Webb. But so the visible spectrum goes from about 400 nanometers to 700 nanometers, which is red, and as you get shorter and shorter down to 400, 350, that's blue and ultraviolet, and violet, And so it only reflects about a third of the total blue light, and then only about 70% of the 540 nanometer green light. And so that just got me on a little tangent one day, asking why metals reflect light in different ways. They, in particular, all metals just have the general property of conductivity. They're really good conductors of electricity, which means electrons flow easily across their surfaces. They're widely shared among the atoms in metals, such that they form, and there's so many cool facts in this little section here, they form a kind of gas of electrons that respond very well to quickly to changes of whether it's photon forces hitting them, electromagnetic energy, or electricity being an electric potential set up across a continuum of metal, in other words, metal wires in a circuit, hooking a battery up to metal wires. If you set up a voltage, chemical, whatever, some sort of potential force, electric force, that easily causes this loose gas of electrons to flow. And it's so cool to think about that in metals, what gives them their property of easily heating up, more quickly than putting a piece of wood out in the sun, the metal is going to get way hotter, way quicker, and it's going to cool down way quicker too. If you put an ice cube or a bunch of ice cubes in a thin sheet of metal versus an equally thin sheet of wood or plastic, your hand is going to get way colder, way quicker from the ice in the metal tray you're holding. So unless you have a resistor or other element in a circuit with metal wires, the force is just going to get dissipated as soon as possible, and that's what causes a short if metal touches metal in a circuit. And it's interesting that this gas of electrons kind of means that the electrons are shared among the atoms in metals, what's called lattices, just metal chunks of metal. At the microscopic level, they're arranged in these very symmetric looking lattices. Gold's distinct color is determined by the frequency of plasma oscillations. Now get this, the distinct, deep yellow, orange yellow, red yellow color of gold is from frequency of plasma oscillations among the metal's valence electrons, so the outer electrons, in the ultraviolet range for most metals, but in the visible range for gold due to the relativistic effects of the orbitals around the gold atoms. Similar effects impart a gold hue to metallic cesium. I tried to get into it. And then that led me down a whole Wikipedia rabbit hole about relativistic quantum chemistry, which combines relativistic mechanics with quantum chemistry, as you might guess, to calculate elemental properties and structure, especially for the heavier metals elements of the periodic table. Yeah, anyways, I won't get into that any further, but it was just amazing to hear, there's the reason gold reflects the yellow and gold colored visible light and infrared light that we can't see so well is, if you keep asking why and go down deeper and deeper into the explanations scientifically, it's because it's how photons interact with the orbitals around gold atoms, and the relativistic effects of the electrons spinning around those atoms creates the characteristics that allow only certain wavelengths of light to interact with gold. Which I know it's, it's in it. It's like, yeah, you didn't really answer that, Rich, but it's, I don't know. It's like the same way I was trying to understand why, how photons can be emitted from atoms and how they interact. And the deepest I got was that protons and electrons have a charge, and they're always oscillating at temperatures above absolute zero, which is essentially everywhere in the universe. Even the coldest recesses of space has a 3 Kelvin background radiation, which is that microwave background radiation. And so all atoms everywhere in the universe, as far as we know, have this residual resonant oscillation vibration about them. And when charges oscillate, an electron and proton being a negative and positive charge, they are essentially accelerating every time they jiggle. Each jiggle is an acceleration back and forth. Whenever there's a direction change in movement, I guess even on atomic scales, that is a deceleration in one direction, slowing down, stopping, and then an acceleration in the other direction. And an accelerated charge emits energy and photons. And that's the explanation for why atoms emit photons, essentially. Which, when I asked, okay, why do they have charges then? I think the furthest I got was one answer said, the actual quote answer was that it's the allowance of the quantum field. And I think that was, at least for now, as far as I wanted to go. So, anyway, so James Webb reflects gold in infrared light well because it's coated in a thin layer of gold. I could have just said that, but I didn't because I'm me. So, 4 instruments. First one's called NIRCam, Near Infrared Camera. It's a 40 megapixel camera. It's an infrared imager which has spectral coverage ranging from the edge of the visible to 0.6 micrometers, which is 600 nanometers, through to about 5 micrometers. And then that instrument number 2 is an associated spectrograph for breaking apart that light that NIRCam is measuring. And then the third instrument is a MIRI infrared instrument, which goes from 5 micrometers all the way out to the mid-infrared range, which is about 27 micrometers. So we have a total span from gold, gold orange, about 0.6 micrometers, all the way out into the mid-infrared, where some of the faintest, smallest, most redshifted galaxies in the universe are going to be. And this micro shutter array is just nuts. It's so crazy. That right there has 65,000 individual, and these are individually active and operating shutters on it. You can see there, I'll put in a video here. You could just see how advanced they are. Here's an array of 4. So wild. And spectroscopy is going to be key. These instruments are very important because it's going to be key for so much of what Webb does. Spectral lines can tell so many things. They can tell the rotation rate of a galaxy through redshifting, the mass of a planet that causes its star to wobble, the speed of hot gas being ejected from a black hole, the mass of a black hole, based on looking at, again, red shifts and blue shifts, the speed of things rotating around it, and being able to determine what kind of mass is needed for that rotation. The amount of dark matter influencing a star's motion was a huge one, and the expansion rate of the universe, because we know that the galaxies are receding from the redshift, and that tells us not only how far they're receding when we are able to find Cepheid variables, and then for distant galaxies we're able to find supernovae, but it tells us, so we know how far they are based on those standard candles, and then we could see by their spectral lines how fast they're receding, which tells us how much expanding space between those galaxies and us there must be. Hydrogen is the most important element in the universe, mainly because it's the most abundant. We look at hydrogen spectral lines to tell us everything, and because that was the first and it still is the most abundant element of the universe, it still pervades the medium, the interstellar medium in all galaxies, and then the intergalactic medium, like we said. And so there's hydrogen lines everywhere, and they actually shift as light from more distant objects. Let me just go right to this. Show you a video here. Can we go back? There we go. So if a light, as it gets emitted, we can see the hydrogen lines, and as it goes through the galaxy there, a galaxy in the foreground between it and us, you can see that galaxy, the hydrogen in that galaxy absorbs a ton of the wavelengths of light. But yeah, it's super, I think that's a great way to visualize it right there, is that as it goes through different areas of the universe, and especially dense areas of hydrogen like galaxies, the galaxy will absorb tons of the light if it lets the thing pass at all. And you see it pass just to, the light didn't go right through the center, or else we probably wouldn't see the galaxy. But galaxies whose light goes around or somewhat through other things has stamps on it, just like this here. You could see this is the original emission, and then as this emission goes through the universe, it gets absorbed, and then absorbed more and more and more and more until it looks like this. So when it's close to us, only redshift of 0.15, it only has a few absorption lines. And then as you get more, 1, 2.4, 3.6, 4, 6.2, you see it gets progressively more and more and more and more absorbed by all the material between it and us. And here's an example. Transmission spectrum. I'll just zoom in like that. Of Earth's atmosphere. You can see oxygen, water, carbon dioxide, methane. They have their own series of stamps. It's not just one specific area of the spectrum, like I said. So an emission line is when you're looking at a black, you don't have a source of light. So if we were looking from here, looking this way, at this cloud of glowing gas that was hit with radiation, UV ionizing radiation from the sun, a nearby star, that's called an emission nebula, by the way. If it's hydrogen and helium and some oxygen too, it'll have all three sets of emission lines. And then if now we're over here looking towards that star, that's how absorption line works. We look at the continuous spectrum, and the light from that continuous spectrum, as it goes through, it gets filtered out, and this absorption spectrum is what we see as the final result that lands on our eyes or instruments. So the key components of what Webb is trying to do is trying to look at very faint light for very long periods of time and have the crispest resolution, the most crispy resolution possible. So it's the gold, the smoothness of the mirror, the precision with which the mirrors individually and collectively are able to be aligned and flexed. And another aspect about the flexing I don't think I mentioned was things get brittle. And we all know things get really brittle when they get cold. And for how cold Webb is, really the amazing feat of overcoming literally physical barriers was to not have the mirrors crack. Not only once they were cooling down in the cryo chambers, but once they are that cold, they're literally flexing the metal and glass of these structures, the beryllium underlayment and the gold coating. And the gold coating is so thin, and it's just nuts how they were able to actually have the material science know-how to be able to not have it crack. But there's also a ton of other aspects of what makes Webb work and get the pictures that it is now we know it's so good at getting. It's not only the precision, the smoothness of its manufacturing, the alignment of its mirrors, but it's the alignment and stability of the spacecraft itself. Webb doesn't actually use rotating or moving parts at all. It's called hemispherical resonator gyros, HRGs, sometimes called wine glass gyroscopes. They measure the flexing vibration of a bowl-shaped stemmed crystal to sense angular momentum. So angular motion. So if you were to flick a wine glass, after you have the vibrating crystal, and if you rotate it in your hand, it actually responds. But anyways, yeah, so it's obviously more sophisticated than that, but that's the general principle it works with. And that allows it to operate in a vacuum, have no rotating or rubbing parts, and so it's virtually never gonna wear out. In these HRGs, hemispherical resonator gyros, they work with the fine guidance sensor instrument to work with the FSM, the fine steering mirror, can tip and tilt a minute amount very quickly to compensate for small motions or jitter in the light beam, thus avoiding the need to point the whole observatory extremely precisely. So what's amazing about the actuators, another thing, is because they're able to flex it in 5 nanometer increments. It took them, 10 days for the actuator motors to be fine-tuned to positions within 5 to 10 nanometer increments. It took them over 1.2 million increments to do this over 10 days. Obviously, because they didn't want the mirrors to crack over having large-scale movements. So it's just everything about this telescope is just hyper precise. I guess that's the best way to put it. Super duper accurate and precise. Even with all this accuracy and precision, the only way they can make good observations is by the location that they sent Webb to. What's fascinating is I never realized Hubble only observes 35% of the time that it's in space, because the other nearly 70% of the time it's dodging things that would obscure its field of view, like the Earth and the moon, and obviously the sun too. What's cool about L2 is that it's one of the 5 mathematically semi-stable points of gravitational interaction between the Earth and the sun that allows for the orbit to stay exactly in parallel with Earth's orbit, and then therefore it sits there and doesn't stay stationary. It's only a semi-stable point in space, so it does need to occasionally burn its thrusters to maintain its orbit, but really not much at all. And as we can see here, the orbit is really massive next to the size of Earth and the moon even. It takes 6 months for it to go around. From L2, Webb has no gaps in observations. So it does in 5 years what it takes Hubble literally 15 years to do. So it's super efficient in that regard. So in August 2019, Webb was able to finally make it to the stage of production where all the individual parts had been manufactured, tested, and retested, and then it was finally assembled at the end, and it was ready to go. It was an entire generation of engineers and scientists' careers. Some, had worked on it for a decade or more, some 20 years. John Mather being the most senior and holding the longest tenure on the project. They literally had their entire careers at stake. So in 2019, of course, this was 12 years after its scheduled original 2007 launch date. So everybody was in the high spirits, and even Congress in the last year upped NASA's total budget by a few billion, or at least a few hundred million, to $21.8 billion or $21.5 billion, adding $800 million to Webb's budget alone to push it through the finish line, the final launch, scheduled in 2021. Then, this was late 2019, then COVID happened. It pushed the launch date back to October 31st. It was supposed to be at the beginning of 2020, I believe. But it was shipped from California all the way down the West Coast through Mexico, South America, and or Central America through the Panama Canal to the East Coast on the Atlantic through the Caribbean and down to East Coast of South America to French Guyana. Part of the collaboration between the ESA and NASA was that we could use this ESA launch pad for the launch of, and the rocket, of course, Ariane 5 rocket, to launch Webb. At this point, with 30 years on the line of preparation for this launch, really, they had the entire month of December, and the launch ended up being scheduled for Christmas morning, December 25th of 2021. A lot of the sentiment was, for instance, John Mather, he was quoted saying, how do you feel about this? And he said, we worked as hard as we could to catch all our mistakes and tests, so we're going to put our zillion-dollar telescope on top of a stack of explosive material and turn things over to fate. And to underline, as one video actually put it, or at least one press release put it, really just the first whole year of observations from Webb are more of a proof of concept than anything. So most all this information, as much as it pushes the boundary and goes well beyond what Hubble's been able to do, or at least adds a ton of new information in tandem to what Hubble is able to do, is really just a proof of concept at this point, where it's not until this coming year, 2023, and then the next year or two after that, that we're really going to be seeing, just like Hubble, again, even after, it was still 2 years before it produced a deep field, 5 years before it had the supernovae observations that it was able to discover the effects of dark energy. At one point I learned that Hubble is the most cited observatory in all of astronomy, and it produces something like 9,000 published papers based on its data every year, and that's since 1990, that was when it was launched, but the lens correction wasn't added until the mid-90s, so 93. So really we're coming up on 30 years of Hubble data, which is tens of thousands of papers produced. And Webb is, no question, going to be exceeding that over the next decade. It's just so remarkable how much data is sitting in these pictures. And one thing I did find, and that I am sure is going to hold true for all of you guys too, is that the more you know about a subject, and especially the subjects in these pictures we're about to show you, the more beautiful they become. They're intrinsically interesting images to look at without knowing anything about astronomy. But then you add a layer, and an ever-increasingly deeper layer of understanding to what it is that you're looking at, based on the volume of knowledge about how the universe works that we've gained over the last couple hundred years, and over the last 100 years in particular. It borders on an impact at the level of at least giving you a connection, a sense of greater connection to the cosmos that we live in. And what is more meaningful than feeling that you have some sort of understanding and comprehension to the way the universe works? So after Webb was launched, there was a period of a couple months of deployment. It's slow release of all the mechanisms and adjustment, and to get it ready. Gunther Hasinger, and ESA's director of science, said there's going to be several days of terror when all these mechanisms are unfolding. The telescope was launched with slightly less speed than needed to reach its orbit and slowed down, because an interesting part is normally a spacecraft, you either have thrusters on the front and back, so that if it was going too fast towards L2, it could just burn the thrusters in the front to slow it down a little bit. But because of the infrared sensitivity on the mirror, the cold side, it can't have thrusters burning heat that would literally destroy the telescope. You also, for the same reason, cannot turn the telescope around and burn the thrusters that are on the back to slow it down. So, because then all those instruments would be facing the sun and burn up. So this was another interesting point. Just all the causes, the potential for error was just, it blew my mind to sit here and learn about, and how nervous these people must have been after 20 years and billions of dollars in pressure from the government. And these technologies so many of them were not proven yet, or they were tested but not actually field tested yet. This was the proof in the pudding. So it needed to be thrust just under the amount needed to get it to L2, and then it would just have these small micro thrusts to continue to burn and correct its course on the way there to perfectly enter it into orbit. The primary rockets fired for about an hour to make the first of 3 planned mid-course corrections. The sun shield took about 3 days, and they were remotely releasing the mechanisms to let them unfurl. And at one point they said that in the first day they were releasing them so efficiently that they just kept going beyond and doing way more than the schedule planned for. But then at a certain point, it was just working so smooth, they didn't want to push their luck. So they actually quit early and came back fresh the next morning to continue to complete the deployment sequence of the sun shield. Because it's, everything on the spacecraft is crucial, but the sun shield, it's not like they had 2 of them. And all the major deployments, all the gross movements of the whole telescope as a whole, spacecraft as a whole, was done all within about the first month after it was launched on Christmas Day, January 7th. They unlocked the port side wings, the left side of the spacecraft if you're looking out the direction the mirror looks. January 8th, the next day, they unlocked the starboard, just to give you a starboard side, give you an idea of how slow and calculated and pre-planned all these movements are. So they locked it in place and began the mirror alignment, the alignment of the individual hexagonal segments to rough positions, and then they could from there begin the micro alignment that I talked about, taking about 10 days to move in 5 to 10 nanometer increments, taking 1.2 million adjustments, incremental movements to move 12 millimeters. At the end of January, at the end of its first month in space, a third and final course correction took place, inserting James Webb into its planned halo orbit around the Sun-Earth Lagrange Point 2 location. Something that I was surprised to hear about was a couple months later, after they've been just testing for the first few months, between May 22nd and 24th, a large dust mote-sized particle struck the C3 mirror. You can see here. One of the things I hadn't realized was just how much dust is moving around. And one thing I guess I was aware of, but you think of space because, it always is preceded by the adjective empty. So often, empty space between planets and stars. We know that, we slowly have started to get an idea, though, that there's tons of gas and then there's tons of larger dust. So even the dust itself kind of has a tendency to be concentrated in areas which happen to affect Webb here, and they have taken action since then. They decided to kind of do a course correction for 2023, so which is going to affect some of the observations. They're going to change it because Halley's comet tail, it's not going to come by. Halley itself won't be back in the inner solar system until 2061, but the bright tail trailing out behind it is filled with dust, debris, and ice shed from the comet. It's that debris that Webb is predicted to enter in 23 and 24. And so what they're going to do is actually rotate Webb so its back is facing going into the meteor shower. And in space, orbits, Webb, anything that orbits in space is going much faster than anything we're familiar with here on Earth, other than, or even bullets. So, probably 1,800 miles an hour. And spacecraft in low Earth orbit go about 17,000 miles per hour. So, almost 20 times that. And then, let's see, how fast is the Earth orbit? $67,000 miles per hour. So once you get on the magnitude and the order of orbits around the sun, you get extremely fast-moving objects. And although most objects are rotating around the sun together, so it's all relative velocities, you're probably not going to be going 70,000 miles per hour relative to something that is near you in space. Sometimes you will be, and even if it's only even if it's still a fraction of a difference at speeds around in the tens of thousands of miles an hour, a fraction of a difference could be 500, miles per hour difference, or even 5,000 mile per hour difference. So even the smallest grains of dust caused an impact. C3 segment that got hit was knocked from 56 nanometers to 258 nanometers out of alignment. But luckily, realignments to the mirror segments using those actuators reduced the overall impact to just 60 nanometers, pretty much what it was before, which is astonishing. That's so cool. Really cool. It's really interesting to just know how much is out there in empty space. And although NASA is able to have some mitigating measurements or take mitigating action towards the dust and predict it and be able to orient the Webb to the extent that it's allowed to not be facing the sun to avoid it, they said that they got plenty of fuel to be able to keep, making unplanned adjustments to the orientation of it. But that's only if a grain of sand doesn't turn Webb into a $10 billion lesson in protecting sensitive equipment. And so we have arrived at the results. So here we got a zoom. We're zooming in from Hubble's image of this 32 million light year distant NGC 628 M74 galaxy, the Phantom Galaxy, which showcases the older, redder stars towards the center to the younger, bluer stars in its spiral arms, where anytime you see spiral arms, that's where the most of the star formation is happening. These large regions of hydrogen gas, a particularly ionized type of hydrogen called H2 regions. And then we're going to see the transition into what Webb is able to add to this image. Look at that. And we can see the maybe 10 to 100, or probably actually 500 light year to maybe up to 5,000 light year across. That blue core right at the center is probably a black hole. It's probably where a supermassive black hole lies. It's so amazing. It's strikingly different. The distinction between Webb's optical UV and Hubble's infrared, somewhat optical view of this galaxy. Webb's highlights much more clearly the masses of gas and dust inside the galaxy arms here, and the loose cluster at its core. And this is actually a pretty common practice in astronomy for astronomers to look at objects in multiple wavelengths using multiple telescopes, because many telescopes don't have, just by the nature of how you have to collect that light. X-rays and gamma rays have to have completely different, I don't know if they're called mirrors at that point, and that's a common thing to get the large picture. Next we have the Cartwheel Galaxy. And this galaxy is even further. It's about 500 million light years away. And the galaxy has two rings here, a bright inner ring and a surrounding colorful outer ring. That's a direct result of a smaller galaxy, possibly one of the two galaxies on the left there, passing through it millions of years ago. And it's presumed that it was a normal spiral galaxy like our Milky Way before the collision. And so it's only now, just now, collecting itself, picking itself up by its bootstraps, and moving on with life after being blindsided. Yeah, scientists think that collision was actually 440 million years ago, or at least before so probably more like 1 billion years ago in proper time here. If it's 500 million light years away, you have to add that. That means what we're seeing now is 500 million years ago. So it took the galaxy almost 500 million years to reshape itself into that. What's always really cool to think about is that in most of these galaxy mergers, based on the star formation they're able to see, or actually lack thereof, cosmologists, astronomers think that a lot of most of the stars in the galaxy pass through the other galaxy pretty much unscathed. It definitely disrupts the pattern of star formation in the galaxy, but it doesn't do a whole lot to any individual star. No two stars, there's so much space in between the interstellar distance there, in between stars, that no two stars ever directly hit, or they rarely do. So the outer rim here we see is due to star formation actually being triggered just by the shock wave of this ring of gas from within the galaxy being exploded out through the gravitational pull of the penetrating galaxy. And it's creating a shock waves that create a burst of star formation that really resembles the shock waves, the continual shock waves that distinguish the arms of spiral galaxies typically. And one thing I don't think I mentioned was that Edwin Hubble was actually if he didn't invent it, he made significant contributions to the classification of galaxies. And I wanted to show you there's essentially only 3 types of galaxies, or really 2. It's just either elliptical or spiral, and then spiral gets broken into either barred spiral, or regular spiral, or some sort of mix in between. And then there is a third classification of galaxies called irregular galaxies, which is kind of a catch-all term. Actually, I have it right here, don't I? Yeah, this diagram right here, we can see this. So we have the Hubble day vacuolars diagram. We have a small irregular galaxies, and I believe they begin slowly rotating, and some end up with a bar shape, some end up with intermediate spirals, and some have very clearly defined spirals like M74, where each of these spiral arms designate intense star formation regions. And just the one really important aspect, I think the easiest takeaway, is that Both of these appear to merge in their evolutionary process into elliptical galaxies in the future. What elliptical galaxies essentially mean most of the star formation is no longer existent. I guess you would either think they're much older, or they are just the nature of the way they were formed, or the amount of mass they have in them, or dark matter maybe surrounding them, led them to cease star formation earlier, or they are just intrinsically older galaxies that have burned most of their interstellar dust and gas into the stellar life cycles already. The Carina Nebula is 7,600 light years away. It's interesting because it's a young star-forming region. And another thing I found that was super cool was to show you guys. Let me stretch this out here. Or you know what, we'll do this instead. Yeah, just type in, well nobody's going to type it in. I forget, I feel like that was such a boomer thing to say. Go ahead and type in HTTPS, do the old click, and find this link in the description. wwtassets.org, click on Webb, for instance, or Hubble even. You will see just how far away and how small these objects on the night sky really are. So it's the scale that of course everybody knows I'm fascinated by. It's the scale and then the just extreme resolution that this shows you here. And I'm going to click the Carina Nebula here. You can see it was focused on the Orion Nebula. And here it zooms in on the Carina Nebula. Just look at that. Look at the detail in that. Look how many more galaxies show up in the background there that are invisible in this image. The stars, anything with a diffraction spike, the 6 spikes coming off it, are stars nearby. The more distant objects, maybe a few of those might be really distant stars in the Milky Way, but most of those are distant galaxies. And then we see what the cosmic cliffs are the outer sphere, the outer membrane of a cavernous interior of starbirth, ionizing, just blowing out ionizing radiation. So they're creating these huge cavities around the young stars that have just, within the last million years or so, which means they're infants on cosmic scales of time. These regions are stellar nurseries. I always thought that's a beautiful poetic term for it, is that's what they are. They're the volumes, these voluminous, like nebulous clouds of interstellar gas eventually collapse, and most of the time these are part of, if we were able to zoom out and get a God's eye view of the galaxy here, we'd see that these are a part of these huge structures that actually create I don't know if this is exactly it, but they are the part of the spiral arms or the bars, which in reality are shock waves traveling in orbit around the center of the galaxy. And that's where most of the star formation in galaxies take place. But on a microscopic scale like this, you zoom in, this is how stars are born. Oh, I guess it automatically turns the filter on for you. This image here, to give you some perspective, it's 7,500 light years away, and this whole image is about 12 light years across. Our solar system itself is about a quarter of a light year. I guess the furthest objects might be a quarter of a light year out there, but we're 8 light minutes from the sun. Neptune is a couple light hours from the sun, and this is 4 light years across here. And so that's the order of magnitude. A lot of these are stars sitting within the clouds that the infrared telescope, the infrared wavelengths reveal about what's going on in there. I kind of misspoke. I guess the general pressure, outward pressure from all radiation from the suns, the bursts, the shock waves of the initial ignition of fusion at these cores of these young stars, that's been going on in most of these probably for tens, if not hundreds of thousands of years. They're creating the overall structure that is kind of this compressed sheet of gas that is the mountain range, so to speak. And then the steam-like stuff coming off it is the particularly hot, the excessively, the hotter, the gas that's hotter than the surrounding membrane of mostly hydrogen, but it could be there's definitely plenty of other elements at play here that's ionized. And ionizing radiation is anything at UV and higher frequencies that actually knocks the electrons completely out of their orbit, whereas optical and infrared, they operate more on the scales of interacting with atoms such that they kick the electrons up in their orbital levels a little bit, and they kind of like make them more excited, but the electron doesn't get knocked out of the atom completely until you get energies on the scale of UV and far UV and ultraviolet soft and soft X-rays, and that shoot the electrons completely out and create almost like a plasma. It's so hot. Let's go back to so this is Hubble here, which is still a very, very detailed image. But then as Webb gets transposed on top of that, we realize just how much more detail. I mean, not only the detail of the outline, but pay attention to the background stars and how many more start to appear in Webb's image. And then you see the fine detail of the structures right here. The pillars are kind of like the areas where the huge sheets of gas haven't quite, they're resisting the outward expulsion of shock waves and pressure of radiation from the stars, so they haven't quite ruptured through. And it's just cool to think of it like that. The protostellar jets and outflows, which show up as gold here, shoot from the dust enshrouded nascent stars. They blow out, a blowout erupts at the top center of the ridge, spewing gas and dust into the interstellar medium. You can see right here. This early period where these early stars are enshrouded in dust and the nebulae still, they only last up to 100,000 years or so. And scientists can take these images and break them up into their spectral lines and see what elements are there. So next we have the Southern Ring Nebula, 2,500 light years away. This is the last. This and the hot Jupiter are the objects within our galaxy here. This is an old star that died and blew away, expelled its outer layer of gas and dust 2,500 light years ago. The near infrared on the left, the mid infrared on the right shows that it's actually a binary system, and it was only the outer shell is from just one of the stars in NGC 3132 here. here we have a great animation of how spectroscopy works as the sun's light passes through the planet's atmosphere. We have, a hydrogen-dominated sun, and then we see these spectral lines appear that we can detect if the planet is oriented so that it passes in front of its star from our point of view. And you can see the wavelength shifts and shifts and shifts as you break it up. This is WASP 96b here, 120 light years away. And we can see the water, different spectral lines here that point to the water that are being emitted here. And these were it's spectral images like this that tell us so much about the chemical composition and the densities and what these and how thick these atmospheres probably are. And then we can see other details about the gravity, the size, the mass, the orbital speed around the star, about these planets. This is all, again, to learn more about our stellar neighborhood and where life might originate from. So let's go ahead and zoom into Stephan's quintet. I believe it was first viewed, observed, categorized, logged by in 1877 by Edward M. Stephan. It was the first compact group ever observed, and he wouldn't have even seen it that well, that sharply. I believe this is from a 4 meter, 2 meters, so it's still really big. It's a 6-foot telescope on Earth, ground-based. I think this is a UV wavelength right here. And then as we increase the opacity, we can see here just how much more detail Webb is able to add. And then the mid-infrared image gives us access to a whole different longer wavelengths. So we're able to see even more, even deeper into the galaxies. These 4 right here, 1, 2, 3, these 2 are interacting with each other. All 4 have interacted at some point. And then this one is the foreground image. This one right here, this is called, let's go up to NGC 7319. Here's a beautiful image taken by Hubble. Well, actually, let me show you this one first. This one over here is taken by Hubble in 1996. I want to give you guys an idea of how Hubble has been able to improve its imaging capability over the last 20 or 30 years it's been in operation. This was 96, not long after the deep field, only a couple years after they fixed the lens aberration on it. And they were able to go from that to this right here in a couple years here. And then in 2009, 10 years later, the astronauts went up on Hubble servicing mission number 4 and installed what's called the Wide Field C3 observed camera that enabled it to look at this Stephan's quintet, or the Hickson compact group number 92, to give this image right here. And we can see just how much more detail you have in here. All these you have a little spiral galaxy off to the side here. Just have so much more resolution. And so now we go from that to Webb. So at 300 million light years away, 290, this group of galaxies tells scientists so much about galaxy mergers. It tells us about how the massive black holes at the centers of the galaxies, what elements are composed of, compose the galaxies themselves, and what's spewing out of them. The blue specks in the spiral arm, going to this one here. The blue specks in the spiral arm here are, let me zoom in actually. Those, it's so far away, 500 million light years away. You would think they're individual stars, maybe really bright ones, but they're actually groups of stars. They're not even individual stars. That's how far away and on how massive of a scale this galaxy exists. The blue dots are younger, the red dots are much older stars. They're clusters of stars, many thousands of stars. Well, if we go here, this group right here, NGC 7318A and 7318B, that's a very closely, actively colliding and interacting group of galaxies. Tons of new star formation going on here. And a lot of these stars, because of the interaction, these stars are less than 10 million years old, which is crucial for scientists studying protostars and star formation in at large scales. From what we speculate is galactic mergers made up most of the universe at the earliest stages. And then NGC 7317 down here is probably the most normal looking of them all. But it's an elliptical galaxy, so it's less affected by the interactions, but it also is redder intrinsically. And then look at that transition to the Webb's image. Now NGC 7319 is the most interesting here because we think it has a black hole spewing matter out of it in front and behind, I believe towards us and behind it. And what Webb has done is actually take a spectroscopic analysis of it to see the composition of what's going on here. This galaxy is a highly distorted barred spiral galaxy that's about 100 million years out from its collision with the local other galaxies there. This is what's called a Type 2 Seyfert galaxy, which is it tells us that, or it's one category of active galaxies with active galactic nuclei, which are quasars, which are really the same thing as just having extremely active supermassive black holes at the center of them, interacting with matter, condensing it extremely and creating a ton of heat and energy as a result, and spewing it out of the poles of the black hole, and far away from the galaxy, sometimes up to millions of light years away, in these huge dramatic jets out from the center, with one of the largest circumnuclear outflows known in galaxies of this type. This outflow, this one in particular, reaches up to 500 kilometers per second and spans 13,000 light years. The star formation rate appears normal for a spiral galaxy at about 2 million solar masses per year. The majority is about 70% of it is in the spiral arms, so that's pretty standard for galaxies of that type. The core appears to be in the ultraviolet band, indicating heavy extinction, meaning extinction of starlight or shrouding by the active galactic nucleus. There's a 3-component radio source too. Radio source with an overall size of about 6,000 light years that's straddling the nucleus. A strong X-ray source with a high redshift has been detected at a separation of 8 minutes from the galactic nucleus, and this quasi-stellar object, and quasar, is most likely being ejected from the host galaxy. These are all the same phenomena, just oriented differently. I think a blazar is when it's directly oriented, directly at Earth. Quasar is when it's at kind of a an oblique angle, and then a Seyfert galaxy is more from the side, I think, and that's how they can tell that it's 500 kilometers per second away. It's because they're looking at the redshift of the lines. So we have the spectra of this galaxy. They're breaking it up, and they're able to see what kind of matter is circling this black hole. They break up the wavelengths. So the medium resolution spectrometer, part of the MIRI instrument, analyzes objects, light spectra here. It's determining what is the chemical makeup of the objects falling into the black hole. So with this data, it helps scientists measure spatial structures, determine the velocity of the structures, and get a full range of what elements, like molecular hydrogen, silicates, which tells us something about the evolution of stars that are producing these elements. And then that's the center. So on the object on the outflow, the quasi-stellar object appears to have, so it's got iron or argon, neon, sulfur, even oxygen in it. Spectrum reveals here that the supermassive black hole has a reservoir of colder, denser gas with large quantities of molecular hydrogen and silicate dust that absorb light from the central region. So that's causing the extinction of light from the nucleus there. And these are all multiple emission lines here. So it's heating up the gas, which in turn, from our point of view, is emitting in bright spikes in the spectrum of its emission, these spikes of emission lines. And I love this part here. I'll have to insert it. I know he's got to be doing it with a little tongue-in-cheek here, but David Butler says he's trying to drive home just how sensitive Webb's instruments are, and he's pointing at how faint of light, of wattage of light Webb can detect, saying that, note the units of brightness here. A Jansky is a very small unit. It's 10 to the negative 12 watts. That's a trillionth of a watt. So a Jansky is a trillionth of a watt, and Webb is detecting 0.001 Janskys. Butler says, picture a dim
1 watt light bulb. Webb can detect a wattage that is 0.0000000000000000001 watts. It's quite remarkable.
Oh, I got a kick out of that. I've seen it like 4 times now watching this video, trying to learn from the master himself, and I laugh out loud every single time I hear that. He just goes, oh, it like doesn't stop. So finally here we got SMACS, what we opened up with. SMACS 0723-73, sometimes with a little J thrown in there. And this guy is the first ever deep field image from James Webb. Beautiful image, and we can see here the transition from Hubble to Webb. And just how much more detail and resolution it is. And it's at these distances that the distinction between the difference, the technological and also wavelength specification or specialization between the two telescopes is really going to be most remarkable. We zoom in, so the bright star at the top left there is in our galaxy. And anything with a diffraction spike, the other couple stars you can see there are in the Milky Way, but the other galaxies in this picture are 4.6 billion light years away. The large ones, and the small ones are even further, between 4 and 6 o'clock, and it spikes. So at the bottom are several very bright galaxies. This is the core of SMACS, the 0723 cluster here. And there at the bottom left, we've seen a galaxy with a redshift of 13.1, which is already two orders of magnitude further than GNC 11 that we mentioned earlier, that Hubble has ever observed. It's just so incredible. So look at the detail of that top one there. Yeah, the detail of that one right there. That's further than the furthest galaxy Hubble ever observed, and it has so much more detail. What Webb is able to do is, they think, go back maybe 20 to even 25, a redshift of 25 possibly. It's insane. Some of these galaxies Webb is going to be detecting in the next year or two is, I'm extremely excited to see what happens here. Yeah, the last little bit here, we can see the arcs. Look at these arcs. These two arcs are actually a double lens of this same galaxy. This is again from the distortion of space-time itself. Einstein predicted this. Equations perfectly describe it. Einstein's field equations, specifically with the Friedman, Lemaitre, Robertson, Walker parameters attached to them, and these parameters are the amount of radiation, matter, dark dark energy in the universe, and if you tweak those numbers, the values of those numbers, the parameters can adjust, and it's by looking at that equation with certain different parameters and different Hubble constants, different velocities at which galaxies recede per light year, per distance, that Webb is trying to confirm or possibly completely destroy, and leave scientists possibly coming up with a new physics, a need for a new physics. In this galaxy, the 13.1 billion light-year-old blob right there, they were able to break it up spectroscopically and see the spikes for hydrogen, neon, oxygen. And what that tells us is that even that long ago, there was already early star formation. So 13.1 billion years old is, let's go back to our, why don't I have that up? I don't know. Come on, Rich. Get it together. Our handy dandy cheat sheet here. Let's see, a Z, a redshift of 13.1. It's right here. That's over 30 billion light years away. The age of the universe would have been about 300 million years old. So this is only 100 or 200 million years after the first stars have formed, and we've already seen how galaxy evolution plays out on the magnitude of, it takes hundreds of millions of years for these galaxies to collide and merge and spew matter out into these structures that have to, from the gravitational force of the nucleus of the black holes. Typically, we think most galaxies have black holes at their center. These things take hundreds of millions of years to coalesce and recombine into anything with a semi-spherical structure. So the fact that we're seeing galaxies only 300 million years after the Big Bang, the origin of the universe, might call for us to, the people I look to for the results here and interpretation of these results, to invent or drastically modify or keep probing deeper until they have a better explanation of and understanding of the physics at the earliest and most extreme conditions of the universe. It's, again, the more you know, the more you appreciate just how much data is being revealed in these pictures here with Webb. Oh, you know what? One aspect of Stefan's quintet that I completely forgot about was that it was actually possibly pierced by that one right here. So this image that isn't in Webb's picture, but this guy right here, it's thought that it went right through 400 million years prior. It bulleted right through there, and it actually has a ring-like structure, like the Cartwheel Galaxy. So it's thought that maybe that one got passed right through and disrupted that galaxy. You could see it, yeah, right there. I don't know, I think it's so fascinating that, you know, these galaxies are frozen in time on human time scales, but if you know, through some deduction, looking at the cosmos at different points in time and at different areas, and we seeing, observing different mergers, we can piece together what is probably going on these scales of hundreds of millions of years, and it's so awesome to watch. This here, where's my video here? Here we see galaxies forming and being evolving over time here. This is on the scale of 1,000 to 100,000 or 1,000,000 Kelvin, and here's like a at the redshift. We see at a redshift of 30. So we think that right here, we think maybe right here is where Webb was able to see somewhere between 25 and 15, a redshift of 25 and 15. Webb might be seeing the earliest filaments start to light up of the universe. And then by 11, we already have galaxies. You can see the nuclei of massive galaxies at redshift of 10. The universe is already lit up with galaxies. But if we're able to find a really quiet part of the sky, that just perfect line of sight through the cosmic web, to have minimal distortion and other noise from foreground galaxies, we might be able to see some extremely distant galaxies, and then on the other hand, we might be able to see even further galaxies through gravitational lensing. And it's cool, you can see the merger of material here and how it would look in optical versus ultraviolet or infrared, highly infrared, microwave even. It looks like an absolute plasma at the longer wavelengths. Then here we go. Here we see the galaxies merging together, and here's how models simulate that they would interact. So the one really, the lighter one gets ripped apart and possibly into this lenticular, circular, galaxy with a core with a concentric circle around it. So this dwarf galaxy next, Webb has made a few other videos here. Here's that. I just want to show you guys because it's just beautiful, and this one's taken with the near infrared camera. So near infrared is always going to look more like optical images. It is false coloring, but it's close enough to the optical that it resembles structures and objects more than the mid-infrared. The mid-infrared is really more like an X-ray because it's getting in there. It's getting to the core underneath, behind these dust clouds. And this one's amazing. It's able to resolve stars inside a dwarf galaxy. 3 million light years away, so 1 million light years beyond Andromeda. It was specifically selected because its gas is similar to that which made up galaxies in the early universe, and it's relatively nearby, so we can differentiate individual stars here within the galaxy. It says the gas in WLM is fairly unrich, chemically speaking, so it's poor in elements heavier than hydrogen and helium, so that's why it simulates the early universe. Next we got the spiral galaxy 5332. This one is another spiral galaxy face-on, and it's a high candidate for lots of interesting information that tells us tons about what's really going on as far as star formation and evolution in the galaxy. This one's about 30 million light years from us, but only about half the size, maybe a third smaller than the Milky Way. So now we got 2 ZW96. This one is a pair of galaxies roughly 500 million light years from Earth, about the same as Stephan's quintet, and lies in the constellation Delphinus, close to the celestial equator, so it's directly above. This one's showing us how galaxy mergers happen. A merging galaxy pair cavort in this image, captured by NASA. It's amazing. Just look how zoomed in this is. 500 million light years away. Just keeps on going. That's a local star. Or local. All these are stars in our galaxy we're looking through. And we could see it right in the middle of being, each of them being torn apart. Still maintaining the top one in particular, the spiral structure, but it's right in the process of being ripped apart, though. It's pretty fascinating. Next we're going to look at the protostar L1527. We could see this again be a super high resolution zoom in. This image is of such a small area of the sky. That's why I love these zoom ins. You really get a sense for how tiny of a area of the sky this image is able to resolve, because in space you can't tell how large or small these objects are. And look at that. Look at how just how much energy it must take to blow that amount off the poles of the star right there. And so we see the structure on the left side here. It shows that this is molecular hydrogen. This is it's saying that there's previous explosions, bursts, and shock waves emanating out from the star as it successfully goes under, it undergoes successively more and more waves of nuclear ignition, and just lets off so much radiation. And of course this is all happening while it's spinning with a high rate of rotation too. So it's whirlpooling and shooting off tornadoes of jets of energy that's runs into the previous layers. What here is previous emissions of hydrogen, and as more and more, as the hydrogen and helium become lithium and carbon and oxygen, and as the star gets older and older, it will hit the previous waves of hydrogen clouds out of which it was birthed, and it lights them up and ionizes them with new radiation, and the structure we can make out because they are heated up and emitting infrared radiation here from the new waves, shock waves coming out of this. So I wanted to go just do a run through, and the remaining part of this video is going to be a run through the 5 main science drivers. And what we're going to see a lot of is in cosmology here for the first chunk of the section, the science drivers 1 and 2, the dark ages, first light, the cosmic dawn, and then galaxy evolution a few 100 million years after that, is going to tell us a lot about how we can interpret what actually happened from the dawn of time to the dawn of the first light of the universe after the Dark Ages that we talked about. Remember, cosmology tries to understand all of space-time on the grandest of scales, and this is currently the Friedman-Lemaitre-Robertson-Walker metric of Einstein's field equations here, and it's assuming, one of the big assumptions of this is that it assumes the Copernican principle like we talked about. And what that is the ubiquity of, the uniformity and ubiquity of the physical laws we understand to underpin the universe, and on the deepest, the largest, smallest, widest, longest, shortest expanses of time and space. And if we run into anomalies, we tend to always hold that to be true before we assume that, even 20 billion light years away, the laws of physics differ. Redshift is the most important aspect, the most important parameter of the largest observations that James Webb is making. Redshifts under 1.5 are relatively nearby objects. They are, again, going back to our scale here. So from 0 to 1, that's over half of the universe's age. Objects at redshift of 1 are already 8 billion years old, and from 1 to infinity, literally infinity, is the rest of cosmic time. So from 0 to 1 and 1 to infinity are the same length of time, but not the same expansion of space. So this is, you gotta keep that in mind when I'm telling you redshifts. When we go from 1 to 2, we're going we're going from 0 to 1 is 8 billion years old, and then 1 to 2 is only another 2 billion years into the past. But as far as distance goes, that increases quite a bit. So 0 to 1 is almost 10 billion years into the past, and then 1 to 2 is a billion light years, and then 1 to 2 is another 5 billion light years or so. There's also some other really fascinating aspects of it, like the fact that at redshift of 1, intergalactic space has expanded so much that the light we're seeing isn't only redshifted, but the nature of that redshifting means that time is slowing down itself. That what we're perceiving from 10 billion years ago or 8 billion years ago, it was happening at twice the speed as we're observing it. It's not a easily observable phenomena or effect because of just how slow things happen on a galactic scale relative to our lifetime. But things like supernovae are definitely measurable. They're on average about 20 days long, and at distances of billions of light years, they are actually stretched out to a period of 40 days. And as you go back in time, they take longer and longer to go through their starburst, supernovae cycle. And it's just nuts for me, it's so hard to wrap my head around that is actually what's going on. We're seeing the universe itself slow down, and which also means that the light from the cosmic microwave background is also probably, given that it's at not a redshift of 1 or 2 or 10 or even 100, a redshift of 1100, which is why it's so redshifted, way beyond infrared. It was originally visible light, ultraviolet light, and way into the microwave region. So I don't know, is it slowed down until it freezes in time? An interesting feature of the earliest of stars, of a universe that doesn't have heavier elements, just based on the knowledge that physicists have of nuclear fusion, is that hydrogen and helium, these very light elements, allowed stars to be, they might have been as much as 100 to 300 times the mass of the sun. And I think the heaviest stars these days are only maybe 50 to 100 times the mass of the sun. Although they can get physically larger, take up a lot more volume, the mass that was in these early stars was very uncommon for today's stars. And this low metallicity that there's heavy atoms cause the early clouds out of which stars formed to break up and disperse into more solar-sized, massed stars. They think today, these days, with heavier elements, with actual what they call metals, anything heavier than lithium, really, anything with more than 3 protons in its nucleus. Just generally, as you get larger elements, the elements are able to be more conductive, and the idea is that higher metallicity of later generation stars is able to deflect heat better than lighter elements, and it breaks clouds up into smaller chunks that will themselves form into smaller sized stars, whereas these early primordially just gargantuan clouds, tens of thousands of light years across, maybe even millions of light years across, started to collapse on themselves, and they didn't have the properties that allowed the heat to dissipate as easily and break up the cloud into smaller chunks, and so they collapsed from these massive chunks that wouldn't really exist today, which is really the exact reason that we study galaxies like the dwarf galaxy and the star formation regions, because we want to understand exactly how, all these characteristics. How large can the clouds be? How small can the stars get? What kind of thermodynamics happens as clouds collapse and they get hotter and they start to rotate and get heat energy built up into them and their momentum. And so these early stars are thought to have been just massive things. And when you have larger stars, you have shorter lifespans as a general rule of thumb. It's thought that this period, 100 million years later, maybe even 150, 200, was when the first heavier elements in the entire universe were formed. And it's this first glow of radiation from these first stars producing the first nuclear furnaces in the cosmos that are thought to spew out ultraviolet radiation that ionized the cooled down hydrogen atoms, so that in that field of hydrogen, the first atoms that had time in the intervening 100 million years of expanding space, dark space, was now being hit. The shock waves of energy and radiation, and ultraviolet radiation in particular, heat up and just inject a ton of energy into the universe. And this was the stage of the universe that physicists or cosmologists refer to as the reionization of the era, reionization era, from redshift of I guess about 6 all the way back to maybe 12 or 13. But we don't know, because now we have candidates as far back as redshift of 16, and it was thought it was around 1 billion years after the Big Bang that the universe was completely ionized. But based on the surprising amount of fully formed galaxies being detected by Webb, and earlier this decade by Hubble, we're starting to think that maybe the universe the universe's star formation and galaxy formation consequently got underway way quicker than some theories suggested. And nowadays, I wanted to bring this up. This is the list of most distant astronomical objects, all galaxies, but it used to be GNZ11 for quite a few years, and now just within a year we already have 3 candidates that blew the lid off that old record completely. Yeah, Webb's new findings are starting to suggest that galaxies would have been coming together around 100 million years after the Big Bang, and previously they thought that star formation hadn't even really begun by then, so there might be more densities, or maybe even something else that we have not predicted yet, some other forces allowing galaxies to come together like this at such an early age. Maybe they have the scale of, or the phases, or the times, or the forces, or the energies completely wrong in their equations. Here I thought this was really, well, all these are really cool. In the first deep field, SMACS JO723, what's called sparklers are possibly the first globular clusters forming around galaxies. So just like we saw the points around our earlier galaxies was in Stephan's quintet, and the other, I forget which one it was, NGC some number in the 3000s. These aren't stars, but these might just be the first globular clusters composed of the first stars ever to exist in the universe. And this is from a paper here. They analyzed compact sources called sparklers, a remarkable redshift galaxy, the sparkler galaxy, at only a redshift of Z of 1.378. But remember, again, when you hear Z1, a redshift of 1 is only 6 billion years old. It's only half the age of the universe. So we got to remember that's still a extremely early epoch of the universe. And so anything beyond a redshift of 1 is potentially still one of the first galaxies ever created, although it might just be a little more evolved than a redshift of 10 or 13 even. So several of these can be identified in multiple images, making it clear that they're associated with the host galaxy, consistent with the colors of quenched old stellar systems. And they say the most natural interpretation of these compact red companions of the sparkler is that their evolved globular clusters are really dense old stars seen at 1.378. If confirmed with additional spectroscopy, because remember that's how they measure the redshift, these red compact sparklers represent the first evolved globular clusters found at a high redshift, which could be among the earliest observed objects to have their star formation quenched. It may open a new window into understanding globular clusters. Not too long after the SMACS 0723, what's called MACS 0647-JD, triple lens. There was a triple lensed galaxy at redshift 11. It's at 3 different orientations, but it's like a little galaxy pair, 1, 2, and 3. And this gives you an idea right here of just how faint these objects are. But if we compare it to Hubble was able to make out these things as just the faintest smears. And with this image, that one of the scientists working on it, Rebecca Larson, said, and this isn't even a deep field, this isn't even a long exposure. We haven't even really tried to use the telescope to look at one spot for a really long time. This is just the beginning. There's these big surveys that the teams that are applying to use the Webb telescope, you have to submit a proposal in this formal scientific paper and hypothesis and predictions to STSCI that then chooses from a pool of candidates. This is right here just gives you an idea of what these surveys do. They map areas of the sky and then come back 6 months later to see if there's any changes, so they can maybe observe either active galactic nuclei or supernovae or anything pulsing at all at that distance. SEERS is one of the 13 early release science surveys. It's designed to, again, these are to not only compare and contrast with old Hubble images to really see what else we can contribute and add and learn more about that objects that are already have been studied for a couple of years now. So it's like they're able to take things that have been extensively studied and now just peel back a whole another set of layers on them. So of course you want to go and look at spots that have already been observed, but there's also motivation to look at new spots too. So some of these are we're able to have comparisons with Hubble. Dr. Finkelstein, he's one of the leads of the SEERS project, saying little is known at greater than 10, and galaxies anything greater than redshift of 12.5 are completely out of Hubble's ability to observe. And a lot of these papers, they make a kind of a tip of the hat to just how great the engineering and therefore the science that will be able to be performed on Webb is going to be. Let's go to defer back to Butler here. Here we can see a spiral galaxy with a large number of blue star forming clumps. This one's only at a redshift of 0.16, so it's only 2.2 billion light years away. It's only 2 billion light years away. And here another one, we have two interacting galaxies at Z.7, a redshift of 0.7. So we're seeing them as they were 6.5 billion light years away, or old. The arrow here is pointing to a supernova. So they're going to be able to, if it's the correct type supernova 1A, they'll be able to determine the distance to that galaxy. Here's another spiral galaxy, also from that same panel. Yeah, as Butler says, it highlights Webb's ability to look at the small scale structures. So 6.5, these are 8.5 billion light years away, and we could see the smallest structures in them. This galaxy is getting further and further away. That one's 11 billion light years away. And then here we crack the redshift 1 at a redshift of 1.4. This galaxy is 9.3 billion from 9.3 billion years ago. We're seeing it at 14 billion light years away. And this one's dubbed the Space Kraken for obvious reasons. Here's a comparison of what Spitzer would see versus what Webb is seeing, and even what Hubble is seeing. You could see just how much better these images really are from Webb. And keep in mind, especially throughout 2023, there are just constant streams of data being looked over and hopefully released soon that might even go back to a redshift of 20, or maybe even further. I don't know, but there's already a paper talking about they're self-aware about not, and they're cautious, I guess, about not announcing officially these high redshifts, but they're saying we might have we have candidates already of redshift 16 and 17, and once we confirm that they're not dusty or just intrinsically faint, we will be able to really tell and officially announce further and further and further most distant galaxy confirmations. Out of over 100,000 galaxies in the Webb deep field, researchers zeroed in on 4 of them and have confirmed now 3 with redshift greater than 10, and 2 of them in the JADES survey here with a redshift greater than 13. These are the 2 most, is it this one? Well, this one at least is one of the most distant galaxies, GSZ13. The PEARLS survey is the prime extragalactic areas for reionization and lensing science. And the main goal of PEARLS is to study the epoch of galaxy assembly, reionization, AGN growth, first light, cosmic dawn. Led by Roger Winhurst of Arizona State. Remember, Arizona was a huge part in building the Webb. This guy was chosen as an interdisciplinary scientist in 2002, so he's been waiting to use Webb for literally 20 years now. So he actually has 110 hours of guaranteed observed time. Their main goal was to spot first light reionization. AGN essentially means black holes, so supermassive black holes. When you hear galaxy cores or active galactic nuclei, think supermassive black holes emitting tons of material actively. Yeah, just to give you an idea, here's the Sears, what's called the North Ecliptic Pole Time Domain Field, and here's all the different galaxies they were able to parse, and a lot of these, they're looking for redshifts, extremely high redshifts in here, and here's what they do is just take massive surveys, or at least as large as Webb is able to do, and they pick out pinpoints from them and try to analyze them spectroscopically and in other ways, and get as much information about the galaxy as possible. So the PEARLS, here's the PEARLS dark field. You could see every galaxy in here is billions of light years away. So this is the El Gordo cluster. This is a famous cluster. Right here is an image of the Chandra X-ray Observatory. Remember, one of the great observatories being transposed on top of a Hubble deep field. And this cluster of galaxies, we can see is this right here is a huge gravitationally lensed set of galaxies. So the cluster right here is actually being able to like exceptionally be accentuated, I guess, by the X-rays that is being mapped in the color gradient here by Chandra, the purple, and let's see. We have tons of really high redshift candidates being lensed, and El Gordo means fat in the fat one in Spanish. Yeah, it's been a source of observation by Hubble for like a decade now. They found some of the oldest galaxies in it. Its mass is 3 million billion times the mass of our sun. Nothing like it has ever been seen this far back in time. And yeah, that picture of Chandra and El Gordo was from 2014 and showed the cluster is roughly 43% more massive than the earlier estimates for it. So this is a huge indication of dark matter here. A fraction of this mass is locked up in the several hundred galaxies that inhabit the cluster, but a larger fraction is in hot gas that fills the entire volume. And an even much larger fraction, maybe 10 to 20 times more, is dark matter. And so the gas here is being ionized and being lit up by the extreme gravitational interaction by all the massive galaxies. This is an instance of what's here, quote, a galaxy cluster having an estimated virial mass close to the maximum mass allowed by the standard cosmological model, the LCDM model. And the cluster is called El Gordo, and La Flaca means skinny, and this little gravitationally lensed strip here is called La Flaca. And here's La Flaca turned on its side. Multiple images of 3 background sources. La Flaca is extremely thin and one of the longest known arcs in the entire universe. It's located between the 2 main mass clumps in El Gordo. It tells you basically the center of mass. And each of these galaxies here, they think these are multiple lenses of the same galaxies. Each color code, the black ones are the same, the red are the same chunks, and the pink ones here. And then this one is the same as this one. It's so amazing. So cool. It stretches and distorts light like that. El Anzuelo galaxy is in the northwestern part of the cluster at redshift of 3.5. And here, again, we have another pair of lensed sources. How cool is that? It's just, I don't know, I can't get enough of gravitational lensing. So awesome. So here, a candidate red supergiant star. They think this is actually a supergiant with an estimated magnification of 4,000. So we're seeing an individual star possibly, maybe a binary, but they don't think that this is a cluster. They think this is at 2.18, a redshift of 2.18, and that 2.1, that would be only 3 billion light years old, or 3 billion years old, and that's looking almost 11 billion years back into time. The color of Kuiper is consistent with a red supergiant star, in contrast to other distant magnified stars, which all appear as blue supergiants. This is in line with the prediction that Webb should greatly outperform Hubble in the ability to detect highly magnified stars with cool surface temperatures. Yeah, look at that. Oh man, that is so wild. From November of 2022, they think that it's been gravitationally lensed, and that's the center of it. So when things line up so that they're perfectly, at the center of one of these lines of warping, at one of the high density points of warping, just like we're about to see with Arendelle, they get exceptionally magnified. And so that's it's the golden egg, or whatever the phrase is, that scientists are really after. Kuiper actually might have a magnification of 15,000. So anywhere between 4 and 15,000. If it's confirmed, it would be the first of many to come. Remember, this is all within the first year. So now we get to Arendelle. There it is, the sunrise arc. So they think this redshift is at 6.2, so it would have been traveling for 13 billion years. It would have been initially in the universe before expansion 3.9 billion light years from us, so it would have already been traveling away from us at, again, multiple times the speed of light. So it's extremely redshifted, but scientists think that Arendelle here might be at the perfect spot in this arc. The geometry of light magnification created by this lensing effect, by the gravity of the cluster in the foreground. It would be in the perfect spot to be resolved as an individual star. This star would currently, with the expansion of space, be 28 billion light years away. It would be 50 times the mass of our sun. And we see it as its journey began at about 900 million light years behind the galaxy cluster. And now here we have Webb's view of the sunrise arc. And stars this massive, remember, they're massive, they have short lifespans because of it. And so Arendelle is long gone now. But this is incredible. This is Icarus previously was the record holder. I think that was the Einstein cross right there, yeah. It was a blue supergiant that was lensed in this galaxy cluster Max J1149.6 in 2011. Again, this is the time dilation effect. Einstein, another one of his many predictions, was he predicted an Einstein cross. If you got, again, the right configuration of galaxies in front of an event and more distant galaxies, and the more distant galaxy had a supernova go off in it, and if you had multiple images of that distant galaxy being created, being lensed by the foreground galaxy, you would have this effect happen right here. What happened in 2011, they noticed a supernova go off, and they saw that that same galaxy was lensed in 4 different places in this galaxy here. Essentially what happened was these 3 images around the Einstein cross lit up just months apart from each other. And so they looked and trained the telescope on it. And because, again, of time dilation, supernovae, especially that far out, this was, redshift of 1 takes 40 days instead of 20. So a redshift of 1.5 would have taken 50 days, I believe. So they had a couple months to go back and check it. Well, the telescope was being used for other purposes, but they found it, and that to me is almost bizarre, that they could see light be sent along different pathways, with each path taking a different amount of time. And we could see images like that, and that we can predict it too. That's a beautiful thing. That's so amazing. And so Arendelle is perfectly split. Right here we have one of Webb's, or one of his stills here. There's a maximum magnification, what's called a caustic line. This is all, I encourage you to see Butler's videos. Just like waves in your pool, and water, ripples in water, and sunlight striking the bottom of his pool, and he uses that example in his video. Now, if you took any still image of that, you would see the bright lines are where the wave crests magnify or they focus the sunlight. And that's exactly what happens. It's this star, Arendelle, along our line of sight, its radiation happened to perfectly fall into a point of highest focal magnification. I think it's magnified 800 times. Between 1,000 and 40,000 times, with about 9,000 magnification being the most likely. Doing the math, Butler says, with this and the size of the image, we get a source object that has a radius of less than 617 billion kilometers. That's 383 billion miles. This is 100 times smaller than the known small star clusters, leading to the conclusion that this must be a single star, a gigantic 383 billion mile wide star. Our star is only a few tens of thousands of miles wide. Yeah, what's the sun's width? Or diameter, I guess. It's, it's larger than that. 865,000 miles. So it's a little less than 1 million miles wide. These stars are 300 and almost 400 billion miles wide. 380,000 times wider than our sun. And going back to the black body radiation curve, Hubble's visible and ultraviolet light indicates that Arendelle is a hot blue star with a temperature between 13,000 and 16,000 degrees Kelvin. Its mass is about 50 times the size of our sun then, and luminosity around 630,000. So now on to the smaller scales, more nearby in our cosmic neighborhood, in our Milky Way galaxy. All the stars, all the exoplanets, and even our own solar system we'll be getting to at the end there. We're going to be unveiling a lot more about the inner workings of the cosmos, because we live in a galaxy, and the the cosmos on the grandest scales is made up of galaxies and groups and clusters and walls and sheets and filaments of galaxies. So it's important to understand what's going on in the center, in the core, in the guts of our galaxy. And that includes everything from the arms, the star-forming regions, and the tens and hundreds of thousands of nearby stars, even within our own, our local neighborhood of the galaxy. And it also includes the entire expanse of up to 100 billion stars in our galaxy. Just think about that, how many stars that really is, and that's in our own galaxy. So we're going to start with stars, starbirths, protostars, star systems, and then the exoplanets around those systems, and we're going to gradually work our way down until we get extremely close nearby in our own solar system. And as far as star formation goes, 100 years ago, scientists didn't even know that stars are powered by nuclear fusion. We didn't know the mechanism really going on in there. As soon as the atom, was discovered, and in the middle of the early first half of the 20th century, when atomic physics was really getting underway, there was a lot of speculation, and Einstein was, of course, central to that, and quantum mechanics, and the understanding of just how different atomic elements might form and how they relate to each other. And once we discovered that, it's probably the fusion of protons that allows for larger atoms to be created. It was definitely stars that were the biggest candidate for how these get produced and how they get merged in fusion, in nuclear fusion. So we've learned a lot in 100 years, and even 50 years ago, a lot of astronomers didn't even realize that stars are continually forming still to this day, and there's generations of stars that are formed out of the remains, the stellar remnants of heavier and heavier elements from prior generations, supernovae and other explosions, and the merging of stars. And what's interesting is that we don't often, we hear of binary star systems, but we don't realize just how many of these star systems out there are made up of binaries. I think it's close to 50%. So almost half of all the twinkles we can see in the night, in the sky with our naked eye at night, are actually binary systems. And there's just so many questions about just the general nature of the star life cycle. How they're created, are they triggered mainly by intense shock waves, or is it, from exploding novae and supernovae? Or is it a more gradual buildup of the pressure transferred to them through radiation, ionizing radiation of clouds and from stellar winds of massive stars? Or do these more energetic processes actually get in the way and kind of disperse clouds that otherwise would have been gradually cooling and collapsing on themselves to form eventually form stars once they reach some sort of limit, some sort of maximum threshold beyond which it was inevitable that some angular momentum in the cloud itself would initiate and would begin a runaway sequence of events that would ultimately end up with stellar fusion at the center of mass of that cloud. And how much of this these mother clouds do stars use up, and how much become planets? Is our solar system, we think, with the sun taking up over 99% of all the mass in it, is that typical? It doesn't seem like it is, in a lot of ways, actually, which is, the more I'm learning about just astronomy in general, the more I'm realizing maybe our solar system is more unique than I had thought before. It seems like there's tons of different configurations of planets, between rocky planets and gas giants, and planets blurring the lines in between those two extremes. It seems like although our sun is a fairly average star, a main sequence star, it's not too dim or too bright. There's also a lot of other possible, again, configurations of life-sustaining solar systems, or at least systems with Goldilocks zones within them in which life could develop and evolve. You could have real nearby, or planets really close to a much smaller, less radiant star, like a brown or red dwarf, or you could have planets much further away, orbiting a larger, more energetic star. Since the 90s, we've discovered almost, 5,000, I think. It's on the order of 5 to 10,000 exoplanets. And as we continue to observe and discover and find out more, which is a huge, again, part of Webb's science drivers, one of its goals. Actually, I got a pie chart here. I probably showed it at one point, but we can see here over 50%, 23%, over 50% is dedicated to galaxies in the intergalactic medium. So how, galaxy evolution on the larger scales, and combined with exoplanets and their disks out of which they form around early stars. And then the other half is, still related. So it's more like 50% of Webb's observations are galaxy evolution, and then exoplanet evolution and characteristics, really. Just because we know out of 100 billion stars in our galaxy, we only know a few thousand systems. Alright, take a look at this. Webb on the left, Hubble on the right. These are the pillars of creation. Remember when I used this as my 5 hours of space facts whispering video? Someone claimed that image right there was a little sus. It's just kind of funny. It kind of is. But it's because there is birth, it is an exceptionally fertile part of our Milky Way galaxy. It's within the Eagle Nebula, which is 6,500 light years away. But in the near infrared here, the pillars here, so this is the standard image from Hubble. This is, then Hubble took an image with the near infrared that made it look more ghostly, saw a lot more going on inside. See all these tips here within, like the crags of the protruding from the pillars themselves, are actually stars. I don't know how, it's got to be 1,000 light years or a few, I don't know, maybe a few dozen light years. But either way, there's tons of stars within this. So just to give you a scale, this is each little pit is kind of a sphere, a little pocket, just like the Carina Nebula. The cosmic cliffs is a pocket from star formation. So any of the bright orange spheres right at the tips, right outside here, I know it's hard to tell what's behind it, what's inside it, what's in the foreground, in front of it, I guess, from our perspective. But at the tips of these, we can say these are where all the most active star birth is happening. Right there, I believe that's one. And then definitely in here, all this infrared radiation is ionizing the cloud. So these are just all these knots of gas and dust. They have sufficient mass, they begin to collapse under their own gravitation, and even during the collapsation, before nuclear fusion ignites, the stars get what kind of leads up to that, the run up into that, is the gradual, the falling in and quickening as they gain or they conserve angular momentum. So as they're far away, they lose their gravitational potential and they collapse, which increases their kinetic energy, translates their potential energy into kinetic energy of faster, just the way an ice skater spins faster if she tucks in her arms. That is the conservation of angular momentum. The densest regions of dust are cast in deep indigo hues, so these are the densest, the most shadowy looking. And then the bright undulating detail at the tip of the red pillar here is hinting at even more star formation. So there's probably tons of young stars in there blasting the inside of those dense pockets of, particularly dense pockets of gas, and they're actually heating them up and they're glowing in the infrared in particular. So infrared is penetrating a lot of these clouds here, but infrared light is also emitted from this whole entire area. But a lot of these stars are estimated to be only a few 100,000 years old and will continue to keep forming over the next few million years. And it does, just so we at least have a sense of the proximity of all these points of light to each other. It says that most of these stars are local, so even more distant stars, even in the Milky Way, and the distant universe here, are both pretty largely obscured by the even further surrounding gas within the greater Eagle Nebula that the pillars of creation lie. So again, Webb's studying this because scientists want to know more about star formation. And one of the interesting things I stumbled upon was brown dwarfs that actually, as of pretty recently, within only the last couple decades, since 95, there were simple, sharp definitions of stars and planets. But this broke down after the discovery of a brown dwarf in 1995. And we've been looking at them in particular ever since, because they may hint at undiscovered mechanisms that we didn't quite understand. We used to think that, even though we know stars form out of clouds and in groups, and we used to think we had a rough understanding of the limits at which stars are able to form and ignite nuclear fusion, under which they just become like Jupiters, even hot Jupiter planets that still orbit around their own star. Yeah, the HR diagram is a big one that helps us conveniently place stellar masses relative to their temperature and luminosity into roughly neat categories. I mean, you could see there's tons of departure from clean lines on the HR diagram here, especially when you get brighter, hotter, higher mass stars. You go up to subgiants, bright giants, and then supergiants. But the white dwarfs, even down here, these low mass dim stars, they kind of fall into a nice, neat trend line. And brown dwarfs appear to really unexpectedly break off from any of these trends, any of these neat categories. Now, most massive stars one of the most massive stars known is Eta Carina in the Carina Nebula that we've seen. Part of the cosmic cliffs is, or that the cosmic cliffs are in, which is about 100 to 150 times the mass of the sun. The current understanding of stellar fusion and astrophysics and what conditions among varying atoms and their isotopes and varying abundances and can allow for different pressures, different energies produced, different it's actually pretty complex, pretty dynamic too inside the interiors of stars. And so you can have lower mass stars fusing different types of atoms, and higher mass stars will fuse heavier atoms. There's a huge scale, but the current understanding based on the metallicity of stars, the stars with chemical or elemental makeups similar to the sun, with elements heavier than hydrogen and helium in them, only have an upper limit of about 150 masses, solar masses, whereas the lower limit is 80 times the mass of Jupiter. So anything outside these bounds would really test the understanding of how fusion actually takes place in the interiors of stars. Like we said, it wasn't even known 100 years ago that nuclear fusion was the driving energy of the cosmos at the cores of stars. Whereas now we understand it because scientists have done the math to see at rough densities using the gravity and they could tell the mass of stars, and of course the looking at the spectra, telling what elements are in there and what's producing the light. And they're able to make models that very accurately predict the observations of stars and the various types of stars, all the way from white dwarfs to main sequence stars to blue, red giants, supergiants. And all these fall nicely. All this HR diagram data falls nicely within current understanding of what our math and our understanding of physics, atomic physics, would tell us is possible for stars. However, we then run into brown dwarfs. Brown dwarfs kind of break the mold. They are able to have nuclear fusion at apparently rates well below the theoretical limit for the minimum mass thought to be necessary to require sustained nuclear fusion in cores. The lowest mass star we know about before we discovered brown dwarfs was the star only about 80 times the mass of Jupiter. I think the lower theoretical limit as far as our physics is concerned is about 75 times the mass of Jupiter. So this star 2 mass J0523-1403 rolls right off the tongue, is the smallest known star undergoing nuclear fusion in its core. And I have a useful diagram here of just how small this star really is in as far as size goes. So one of the largest known stars as far as volume goes, you could see Scuddy there. I call it Scuddy. It might be Scooty. UY Scooty. Scooty sounds a little sillier. Next to the sun, makes the sun look like a pinprick. And then we blow that up 10 times, and we see just how massive UY Scuti is next to the sun. And if we blow that up 100 times, we see at the sun at this scale, we wouldn't even see 2 mass. We'll just call it 523. And then we have to blow it up to the point where the sun's surface looks flat, essentially, to be able to even start making out the diameter of 523 here. UY Scuti is about 10 times less than the mass of Eta Carina, but it's has a massive radius because it's probably so diffuse. So it's only 10 times as massive as our sun, but it's that much larger. We see right there. But then we have brown dwarfs that are all the way down to only 13 times as massive as Jupiter. They're not massive enough to sustain nuclear fusion of hydrogen into helium in their core, but they can diffuse, or they can fuse deuterium, which is an isotope of hydrogen, and some are able to fuse lithium. So it's interesting that you have these different combinations of atoms, or different types of atoms have different criteria for fusion and different pressures and energies at which they can fuse. And I guess deuterium and lithium in certain abundances or ratios can fuse more easily than science expected. So get this is really interesting that it wasn't until 2010 that 2 binary brown dwarfs, Lumen 16A and 16B, otherwise known as WISE 1049, from the Space Telescope WISE, were discovered to be the 3rd closest star system to us, after Alpha Centauri, Alpha and Proxima Centauri, and Barnard Star, being only 6.5 light years away. So we've known for over 100 years, over a century, about Barnard Star and the Alpha Centauri system, but we didn't know until, as of the time of this video, less than 12 years ago, that there were stars even closer to us. So to me, that's one of the really interesting frontiers of astronomy that's still wide open, is all these very dim, quiet, unexpected objects that are out there. Whether it's small black holes or even supermassive black holes that we're about to talk about, like our supermassive black hole at the core of our galaxy that's unexpectedly quiet, or really small but still significant star systems, or even quiet dark asteroids and comets that all of which we have a serious interest in knowing more about. So this isn't these aren't James Webb images, but I believe Webb might at some point try to observe it. Here you can see a video of these binary brown dwarfs dancing around each other. And this one in particular is really cool, because you can see how we're actually able to observe their proper motion across our night sky over the course of a couple years here. And you could see the 2 stars orbiting around each other and kind of around and the system itself has kind of a orbit. And there's a picture of them both. So I think there's even a smaller object than this brown dwarf system next to us that's a little further away, but still really close to us, even within our galaxy, only 19 light years away, in the constellation Lepus, called Gliese 229b. It's only about 20 to 50 times the mass of Jupiter, orbiting the star Gliese 229. You can Let's see, here in 1994, the Palomar Observatory discovered it, and Hubble followed up on it a year later. So those are just two examples of really unexpected stars, and only within the last 2 decades or so we've discovered these, that they're out there. On a much larger scale, the supermassive black hole at the center of our galaxy, like I said, is very quiet. So you can see data here that clearly shows there's a ton of mass in a very dark, dense point at the center of our galaxy, around which a lot of these stars orbit extremely fast. So we know how large the object must be. And it's a huge mystery for astronomers how quiet it really is. It doesn't seem to be consuming nearly as much material as the other black holes we see even in similar, galaxies nearby. And we're not really sure why. So obviously that's another point of observation that Webb will pinpoint at some point in the future. Previous research has indicated that the mass of Sag A star, Sagittarius A star, ranges on the low end of normal for galaxies as big as our Milky Way. And Webb's going to help determine why that is. We can solve the cosmic chicken and the egg problem here. And at its heart, and the dominant force in that area of the galaxy, is the black hole 1 million times the mass of the sun. It's interesting. It's really actually beyond interesting to think about, is that if we were at a star system in the center there, the entire night sky would be lit up as though we had, 20 moons, full moons in the sky at night. Yeah, the night sky stars would be 1 million times denser than what we see here. And the closest star to our sun is 4 light years away. Where stars in that region, that 10,000 light year central bulge of the Milky Way, are 100 times closer together. So night would it would really just be this grand field of glittering, shimmering points of light in a black abyss behind it. It would just be something to see. And our Milky Way is orbited by, we have the Andromeda galaxy 2 million light years away, which is even larger than the Milky Way, so that's its own galaxy. But large galaxies like us and the Andromeda galaxy have oftentimes their own kind of minor galaxies filled with, we have roughly 100 billion stars in our galaxy, and they have these what's called globular clusters that we mentioned before. And these aren't quite galaxies, but they're their own entities with just a few tens of thousands of stars usually. So they're not quite big enough to be categorized as their own galaxies, and they often are in real close, like satellites of larger galaxies like the Milky Way. And we have a couple called the small and large Magellanic Clouds. And I believe we have a couple, there's actually quite a few. So Webb is also going to study giant stellar globular clusters around our Milky Way. And what's cool about these is that they contain the oldest stars in the galaxy. And there's, if I could find it, there's some relationship about the location of stars and star clusters in the galaxy and how young and old they are in their orbit. So I believe the current model of our Milky Way is that we have, remember, population 3 stars. It's kind of counterintuitive. Those are the first stars to exist. That's the first generation. So population 2 is the second generation after that. They're formed out of the remnants of the first extremely large, low metallicity stars out of hydrogen and helium that have fused into heavier elements. And then our sun is a population 1 star, what we think is the most current generation of stars. Milky Way, just generally, the youngest population 1 stars that, like our sun, are in the central disk, and they're bluer and they have heavier elements, whereas the stars that have more eccentric orbits that aren't perfectly in the flat disk, they are either in globular clusters or they just have more orbits at a higher inclination off the central plane of the Milky Way. They tend to have lighter elements because that was just the makeup of the elements earlier in the universe, from the origins to more like 10 billion years ago when they were formed. And they're redder. They're older, redder, burning much more efficiently. Our stars, I think, with heavier elements, it depends on the size of the star. Larger stars, just as a rule of thumb, have shorter lifespans. Smaller stars, much smaller than our sun, white dwarfs, red dwarfs, they can apparently burn for trillions of years, or hundreds of billions at least. So their light is intrinsically dimmer, and these old stars are kind of in a halo. There's much less of them, but their orbit's much less confined to the central disk, and we think that dust, as much as 15% of the Milky Way's mass. So it blocks our line of sight to a lot of the stars even in our own galaxy. That's again why part of the motivation to make James Webb focused on infrared light. Given that there's so much gas and dust, and there's continual star formation in our galaxy, we know that there's continual planets being formed around those stars. And as far as we know, the data is showing a radically upward trend line of there being no end to the number of planets we can discover in the future, because as we discover more stars, we're learning and analyzing those, we're learning that most stars, if not all stars, have at least some planets around them, and a surprising number of stars have Earth-like, or at least Earth-sized, something approximating the rocky, more terrestrial planets like Earth, our four inner planets, Mercury, Venus, Earth, and Mars. This isn't Webb. Again, Webb is only a year out as of this video here, but this is a phenomenal series of images from 2015 to 2018, seeing this imaged exoplanet. This is actual data right here. This isn't a computer simulation. It's really pixelated, but we can see when that star's light is blocked out, you can see the slow rotation of the planet. And then down here, we have 4 different planets that we can kind of resolve in this image here. And there's a growing list of directly imaged planets. That's just so cool. Until the 90s, the only planets we knew, this is something to think about, that existed in the entire universe were our own planets, all the way out to Pluto at the time. And then in 95, the first exoplanet was discovered, and really that opened the door for a flood of exoplanets in the following years. Once we knew it was possible to detect them, we spent a lot of resources, a lot of money, directed a lot of resources towards the further exploration of more and more planets. So in less than 3 decades since then, we've discovered thousands and thousands of planets around other stars nearby, and we really only probed, again, not far out. We can't see beyond 10,000 light years in the optical wavelengths, but we've only probed around the first, couple dozen light years of around us in the Milky Way here. So we don't know, and they might not frequently evolve into the perfect Edens of Earth, but if there are as many as 1 billion planets in our galaxy as we think, once you get on the magnitude of billions of planets, that there's something similar to us out there. And that's the ultimate objective of Webb and its planetary missions, is finding planets orbiting the habitable zone of their stars, where it's possible for liquid water to form, because we do have a bias, but we also think that there's only so many configurations of chemicals and temperatures that allow complex life to exist, and so that's where we're looking. I thought this was a really cool visualization here. So if this green belt right here is our sun's habitable zone, we see Earth and Mars just inside it. Then we go to a planet, a star, just to give you an idea of the variability of stars that have habitable zones around them. All stars do, because of course all you have to do for hotter stars is move further away or closer for dimmer stars. But it's the likelihood of large stars, being that they have such short lifespans, is much smaller, so having planets around them that have life. So we are targeted on, focused on smaller stars. But just to give you an idea, so UY Scuti, relative to our habitable zone, its orbit, its diameter goes all the way out to, I think, it goes out to almost Jupiter, probably around Jupiter or Saturn's orbit. That's how large the star is. And then the habitable zone outside of that would be, it looks relatively like it is as far away from that star as our habitable zone is from our sun, our star. And to give you a scale, that's Pluto right there. So that gives you an idea of just how much radiation, how much heat is actually pumping off of that star right there. A lot of the information we can gather about planets is through spectroscopy, like we said, with the transit method, and having a coronagraph where you can, like this GIF here shows, you can block the starlight out so that it allows the remaining light, which is, up to 10 million times as dim a lot of times, because it doesn't have its own intrinsic light, or it will have radiation in infrared, but just ridiculously more dim. So it's really remarkable how much information we can glean from indirect methods and then more direct imaging of the actual star. With the transit method, we can also detect their radius. If there's a dip in brightness as the planet goes right in front of their star in relation from our point of view, for instance, for Kepler 186, it was known that the star's disk area has an area of 416 billion square kilometers. And so Kepler detected for its planet F, Kepler 186f, a 0.042% drop in brightness, which means that the radius of this exoplanet is about 7,400 kilometers. And on top of that, we have collaboration among telescopes that can tell us the gravitational tug on the star by the planet, which gives us roughly to a pretty precise number, the mass of the planet. So between the mass and the radius of the planet, we can get an idea of its density and its surface gravity, and then with the spectra we can see maybe what its atmosphere has or is composed of, and what's really cool for the spectra is that for Webb in particular, is that the infrared wavelengths, the molecules and atoms have the largest number of spectral features in the infrared wavelengths. So we know exactly where they're supposed to be, which tells us when we see certain patterns what elements they are, but it tells us a lot of other indirect, it implies a lot of other information, all the way down to its seasons, its rotation, possible weather, climate patterns on it, and even vegetation. If we're able to tell any byproducts from life, or plant life or animal life, and even if there's advanced civilizations, of course the window is going to be super, super tiny. I mean, within 100 years, with all the technological development we're going through, we probably won't be producing any detectable exhaust or any other chemical byproducts too much in the atmosphere. So we're not going to, in other words, for more than 200 years out of our 5.6 or 4.5 billion year lifespan of our planet as of now, really the atmosphere of anyone observing our planet from a distant star system won't have really deviated very much from the natural atmosphere, and they would have to be really lucky. But again, although those odds are low, when you scale that up across billions, maybe even 10 billion planets, possibly, as our telescopes get more and more advanced, the odds start going back in the other direction in our favor. And we're learning one thing, is that many star systems, like I said before, aren't like our own. And it used to be assumed that they were, but now we're saying that the parameters that our star system gives us to work with a certain, the inner planets being all rocky, terrestrial, smaller mass, and the way they're spaced out, and the outer planets all being gas giants, the furthest ones being ice giants, and that much larger masses are actually possibly very unique, or not very unique, but at least there's many variations, and the parameters for what constitutes different planetary dynamics around other stars are way more diverse than we realized. One of the first exoplanets ever discovered was a gas giant orbiting a sun-like star nearby, 51 Pegasi. It whips around its star, a gas giant, in only 4 days, versus the 12-year orbit of Jupiter. We even have other oddball examples of exoplanets that orbit binary systems outside the actual system, so its sky would be absolutely a Tatooine-like sky with 2 suns. There's 5 exoplanets that are part of a compact but stable system, but with none that exceed the orbit of Mercury. And one of them is the TRAPPIST system we'll be talking about, where there's, I think, all 7 planets are within the orbit of Mercury, so that's a huge difference between our system. But the TRAPPIST star is so much dimmer and smaller in radius and mass and luminosity and radiation it gives off that it's 3 or 4 of those stars, even though they're that close within the orbit of Mercury, a couple of them are in the habitable zone. Planets orbiting failed stars even. So we really want to know, are we alone? I think the day we discover signs of alien life, whether they're extraterrestrials, whether they're advanced civilizations coming to us, obviously with some sort of agenda, or completely indirect signs of just organic life somewhere else on a distant system, planetary system, we aren't going to view our reality, our existence, the same anymore. It's going to really change our paradigm. One of the great unanswered questions about our own existence is how Earth's liquid water came to be. There's we're unique even within our own solar system here, but other systems are going to tell us, or at least give clues to how we got that way. So scientists propose that maybe there's a few different ways. Either it formed as part of our planet's primordial disk, and it was coalesced just onto Earth because it was within our same orbit, and Earth eventually attracted all the dust and ice and other debris from around its roughly same distance from the sun gravitationally. Or it could be delivered by ice comets coming in from the primordial, much colder halo formed out of a gaseous cloud of water molecules and among other molecules. As they impacted our early Earth, they just kept delivering more and more water, which would eventually get mixed up in as heavier objects like iron at our core and the rocky components of rocks in our mantle sink in water. Water would of course float to the top and be expunged into our atmosphere and eventually rain down as oceans. Or hydrogen was bound to another atom like ammonia and later broke down and recombined with oxygen in our atmosphere through millions, hundreds of millions of years of atmospheric climatic changes that rained down that water that we currently have. So it's really cool to know that there's so many different ways that water could have arrived here on Earth. And a water molecule consists of two hydrogen atoms bonded with an oxygen atom. Earth contains a lot of oxygen, but hydrogen gas is scarce. So hydrogen in our atmosphere that isn't bound in a molecule, it tends to escape into space, too light and energetic for Earth's gravity to take hold of it. For hydrogen in Earth's early history to have arrived and stay put in great enough amounts to bond with oxygen and make water, it must have been attached to a carrier. That's where the ammonia aspect comes in. And then what do exoplanet biosignatures look like? When we're going to look at them, oxygen is an obvious one. It's so reactive, though, that tells us something if we detect it. It's unlikely to be found unless there's a constant supply of it being pumped out, for instance, from plants like us, like our Earth here. So a biosphere doing photosynthesis would be one cause of finding an oxygen-rich atmosphere, which is definitely detectable, possibly by Webb. It's one of the things that are smart to look for, and astrobiologists are thinking of, what are the things that aren't going to be mistaken for life that might just have other reasons for existing. So oxygen is one of them. Astronomer Heidi Hamill says it's not going to be a single gas. It's going to have to be a combination of gases in a configuration that tells us they're in a disequilibrium state. They can't have formed that way naturally. Astronomers say the telescope is performing 10 times better than expected at observing exoplanets too. So all across the board, Webb is just outperforming the expectations, which is amazing. So from the Quanta article, a really great article written by Natalie. Jonathan O'Callaghan wrote this one in particular, but there's another great Quanta article I've been quoting. I'll have it in the description. Astronomers say that, O'Callaghan writes, say that the telescope is performing 10 times better than expected, and he interviewed Dr. Hinckley, and Hinckley's team sought to test and characterize Webb's ability to see the planet called HIP 65426b by pointing it at the fast-spinning star, HIP 65426. So, and Hinckley says, in my mind, this is the greatest spectrum ever obtained of a substellar companion. We've never seen anything like it. The NIRCam instrument is what they used. They were able to mask the star using the coronagraph on the instrument. And this contrast and separation between the star allowed the separation to see its planets. And then down here we can see, so these are in purple here, the star is completely masked, so everything you see here are the actual planet. It's a direct image of it. And the F300M and F444W, these are different filters that they use to look at different specific smaller ranges of the wavelengths within the more broad near infrared range of wavelengths. And what they did was, you can see here the star right there. You see as the star is dimmed, they're able to see more photons coming from the companion, the planets around it. And so they take the observations and then they digitally remove the photons coming from the actual point where the star is located, and then that leaves they're able to subtract it from the image, leaving only the photons coming from the planets. They said, O'Callaghan says that it's a significant advancement in direct imaging techniques because it's a process in which a second image of a comparable star, or of the same star taken at a different angle is then subtracted from the original. Kepler, launched in 2009, was a huge exoplanet searching telescope that specifically searched for Earth-sized stars, around sun-like stars in the habitable zones around them. And the result was that 20 to 50% of stars are likely to have rocky exoplanets, like we said earlier. It's astounding that out of the sample we've collected, which is growing to a substantial sample size now, which tells us that the larger our sample size gets, the more secure, the more safe it is to extrapolate that across the whole Milky Way. And unless we see a significant deviation from this percentage here, we can assume that 20 to 50% of the entire 100 billion star expanse of the Milky Way has rocky exoplanets in their habitable zones around the planets. And that is promising for detecting life in the stars. Yeah, Kepler alone discovered that within 1,000 light years of Earth, just 1/100th the distance across the Milky Way, maybe even less than that, there's 30,000 not just planets but habitable zone planets. WASP 39b is this famous spectrograph we've been seeing, and it's so famous because it's showing us just how well Webb works. The star is amazingly 700. I didn't realize it was this far. This thing is 700 light years away. So our nearest star is 4 light years. That brown dwarf system is 6.5. This one is 100 times further than lumens, the brown dwarf system. And we're getting data, extremely accurate data. Astrophysicists working on the WASP 39b survey here said that we're really just scratching the surface. And these measurements of this precision was unimaginable even a decade ago. And to put it into perspective, I have this map, this star map here, within 50 light years. These are just the visible stars. So this is just the nearest, and that definitely doesn't mean brown dwarfs, or definitely doesn't include brown dwarfs and any faint, really even white dwarfs. This map is only the stars visible with the naked eye, which is only about 10% of the stars that are actually in the same volume of space here. So all the dashed lines mean it's below the plane, solid lines mean it's above. We have Alpha Centauri right there. And there's our sun at the center. And just look how many star systems. And remember this 10 light year span here, which has maybe 20 stars or so. That's only 10%. So it might have, 100 stars within 10 light years. And you multiply that up, our galaxy isn't a sphere, so we can't exactly multiply it. It's not a linear correlation, but it still is very close to the same magnitude of stars that exist in the galaxy. If you take that 10 light year chunk and expand it up to 100,000 light years, so you multiply it by 10,000, you're going to get an idea of just how many stars there are in the Milky Way. There's 133 stars marked on this map. Most of the stars are very similar to our sun, and many Earth-like planets are actually going to be around these stars. So there's roughly 2,000 stars, but most of the fainter stars are red dwarfs in this map here. So scientists want to know a lot about the formation of planets. They want to understand where rings and gaps appear. They want to understand how planets move further away in their orbital radius from their stars, and how they cool down and contract after forming. They want to know how Kuiper belt objects like our solar system has, our sun has around its distant, way beyond that Pluto might be a really nearby massive member of, and from which a lot of comets come from, a lot of asteroids. They want to know about comets and the asteroid belts in between Mars and Jupiter better, so they want to understand the entire array of different types of solar systems out there. One Webb observation team is going to plumb the depths of Jupiter HD 187733b, which has been observed before. It's so close to its star, its orbit only takes 2 days. That's insane. These super Earths and mini Neptunes that we talked about are the most common planets in our galaxy, and we only have a few atmospheric measurements of them, so the persistent question of habitability, of course, is hovering in the background of all these experiments, and particularly regarding these super Earths, which will have gravity probably a lot more than Earth, but not quite as much as, Uranus and Neptune. So it'll be, there would have to be some beefy Neanderthal-like aliens if they evolved on that planet. Real thick bone density to counteract the gravity. I'm sure they'd have some pretty chunky ligaments too. Probably not a lot of basketball going on those planets. And here we arrive at TRAPPIST-1. It was discovered all the way back to the year 2000, late 1999, I think, but it was ignored until just a couple years ago, in 2017, by the European Southern Observatory. Here's an awesome video of a journey out to TRAPPIST from Earth. When NASA announced in 2017 that it discovered TRAPPIST-1 hosted the most Earth-sized planets found in the habitable zone of a single star, exoplanet hunters were obsessed, and they have been ever since. So this obscure star, pinned in the early 2000s, just sat really in an innocuous, ultra-cool red dwarf star, only about as wide as Jupiter, and less than 10% the mass of the sun. Also, so it's only 40 light years away from us. Remember, we just saw they were able to get really detailed. Webb was able to analyze a sun, or the hot Jupiter WASP 39b, 700 light years away, so almost 20 times further than that. So in a 100,000 light year galaxy, this is a prime target to get good observations of, and they just did. So here's an example of a super Earth here around Barnard's star. But what we're going to see next are the TRAPPIST planetary systems, and we'll see they're way smaller than the super Earth. The initial discovery of its first two terrestrial planets were based on observations from how it got its name, the transiting planets from the Belgian observatory or mission called the Transiting Planets and Planetesimals Small Telescope at Lucia Observatory in Chile. It was just an anomaly at first, but then they found 5 more planets, TRAPPIST A, B, C, and then D, E, F, and G. D, E, F, and G here are the ones in the habitable zone. They're possibly hospitable to life. I believe they weren't found to have very thick atmospheres, so there wasn't any remarkable headlines that were jumping off the research papers here for this one. But nonetheless, it's the existence of the planets themselves in the Goldilocks zone, where water can form rather than be too close to burn off in the steam or too far to be all iced over, is just stunning. It's extremely promising. Spitzer actually played a huge role in uncovering the first stars from the system. It spent 1,000 hours staring at TRAPPIST and was able to tell us there were, identify 7 planets. Then the rough mass and radius of each world, their densities, and slightly less dense than Earth. So it would be interesting to see a super Earth that had a less, smaller density, which would almost be equivalent to our sense of gravitational acceleration on the surface of Earth here. It's presumed that the gravitational motions between the planets, a lot of them were, I think all of them were between, smaller than the orbit of Mercury. But so they were all so close to one another that they had orbital resonances, and they were tidally locked. Here is an example of orbital resonance. Io has the 1-to-1, so for every 1 orbit of Io, Europa has a half orbit, and Ganymede has a quarter of an orbit. Or the other way around, for every 1 Ganymede orbit, Europa takes 2 orbits, Io takes 4 orbits. Here's a diagram of how dim the star of TRAPPIST must be for all these planets to be so close to one another that they make Mercury's orbit of, see, Earth is 90 million miles from the Sun, Mercury is something like 20 to 30 million miles from the Sun, and so these must only be 2 or 3 million miles, which is incredibly close. So they're, even though, I always try to emphasize this, the space, the physical distance between planets of systems, especially our system, is really, really, 20 million miles is a long way. 2 or 3 million miles, or even maybe just 1 million or 2, really isn't that far, given that the moon is only 250,000 miles from us. If there were other planets as close to us as Webb is, out at L2 at 1 million miles away, or really not that much further than that, then you could see something with the mass of planets they have over billions of years, or even hundreds of millions of years, they've evolved into having orbits that are in sync with one another at these particular resonances that we see in our own solar system, and a lot of times in other systems too. Proxima Centauri, for once, is almost assuredly locked either in a 3-2 spin or completely tidally locked to each other. Proxima Centauri, the exoplanet Proxima Centauri b around Proxima Centauri, 4 light years away from us. Yeah, the orbits of these planets TRAPPIST are only in the range of 2 days to 3 weeks, so they're extremely fast years. A 2-day year is pretty fast, even though it's, the older I get, it's kind of seems like it's kind of approximating that for me. So does this tell us anything about life? Probably not. It's telling us a lot about exoplanets. That's a good diagram here of Jupiter, and the diameters of its moon's orbits are really only a little bit smaller than the diameter of the TRAPPIST exoplanets around its sun. And here's an example of actual data that they posted in the report of the planets and how they dip the brightness of the star. As they line up, they dip more. There's a huge dip right there, you see? When the two or more planets perfectly line up. This one is in particular studied so in depth because they transit in front of the star. Their orbits are perfectly oriented towards, so that they go in between the star TRAPPIST and Earth. But even so, even for tidally locked worlds, there could still exist life on the boundary between day and night, where there might be some relief from the extreme heat and extreme, ever-present nighttime ice age on the other side of the planet. There might be rivers of flowing water constantly flowing from one side to the other and then being vaporized as steam clouds and rained down as snow on the other side. Could be, which is really cool to think about. Webb has the near and mid-infrared sensitivity to be able to observe virtually all known Kuiper Belt objects. And Mars is huge. We want to know the life cycle of what water currently exists and what the current atmosphere and what we can kind of glean from looking at its current state in infrared light and about its history and the past water flows that it had and may still have underground, even if the surface water had long ago evaporated. The evolution of global dust storms and cloud systems and dormant volcanoes. Does it reveal a more habitable past? Yeah, if Musk is successful at colonizing Mars, he really, really wants to, and this is so cool that that's a goal. It's a philosophical justification that he's not only extremely self-aware of, but he's also very public about. And I think he's so public, and it's so beyond most people's understanding, myself included, that it doesn't really, it's almost comical how he is so transparent about his motivation that people think he's playing a game, I think, but he is very eager to do his part in saving the civilization that could easily come to an end from either an unexpected asteroid impact, which is what the DART impact experiment was all about, we're about to talk about, or, our own stupid mistakes of nuclear war, or a number of different things. A super volcano could erupt at any point. Probably not likely, so don't wake up too quickly from your slumber if you guys are drifting off here. But they are, in the next 100,000 years, possibilities. And if in the next 1,000 years we don't actively try to colonize and distribute humanity away from Earth, then we're going to, if a planet-wide cataclysm happens, We risk the possibility of snuffing all intelligent life on Earth out. All the traces of humanity gone. And that would be a sad thing, especially since we don't know that we're not the only organisms in the universe that have reached this level of complexity and thought and self-awareness, consciousness, and development. The final thing I want to talk about is the DART impact. This is the collision, the final 5.5 minutes leading up. And this is actually sped up. This is sped up 10 times faster than in reality. But the last frames are actually, I thought they were extremely slowed down. The last frames right here are actually in real time, right there. That's actually how fast it approached. And then the last one right there. So if we slowed that down then to 75% speed, this is 525 feet across, 160 meters in length. And Webb and Hubble got a really good view, and it wasn't Webb, but there was another really good video, I think it's at the end of this, that shows the Atlas telescopes. They show the plume of debris that came off this asteroid bearer right there, and it plumes off. And we're going to measure whether or not it deflected, or of course it will have imparted some momentum, so it did deflect the asteroid, but we're just simply seeing how much force and how much mass a telescope has to be, or spacecraft, to deflect asteroids of certain masses by certain angles in the sky. The final image, this is the impact recorded by Webb right here, which I guess tells you something about the energy behind it. But this final image here, and look at, to me that's so cool. This is right there, this final image here is about 51 feet across. DART's impact occurred during transmission of the final image to Earth, resulting in a partial picture at the end of the movie. So it only was able to send. It's sending it in real time, and it got a couple rows of pixels sent, or maybe a couple hundred or 1,000 even rows of pixels sent. Wasn't able to record, or at least transmit the rest before it shattered. So it resulted in the partial picture. And Didymus, it's a binary pair of asteroids, Didymus and Dimorphos. Didymus is 2,500 feet, Dimorphos is about 525 feet in length, diameter. And they're going to now measure how much that deflected the asteroid. Just like Giacomo and Illingworth back in the 80s, even before Hubble was launched into space, we're already thinking about what's next in planning the Webb telescope. There's already future telescopes in the works. There's already plans on building future larger space telescopes that go back, and now where Webb had a small overlap with Hubble in as far as the radiation band it covers, being the infrared. As Hubble gets more and more obsolete, and our technology gets better, and our rockets get better and larger, and we can launch heavier, larger telescopes into space, we are considering, and here's what the Ariane 5 rocket that launched Webb looks like. And you can see the spacefaring. was 15 feet across, I think. And Starships is, it looks like it's almost 3 times that, so it can fit a much more massive telescope in there. Here's the Ariana 6, brand new updated version, but still not much. I don't think it's any wider. Here's the old USSR. This was almost as wide as Elon Musk's spaceship, but I think this was just a concept. They didn't ever fully develop it. Then we have the Falcon 9, Falcon Heavy, which is multiple Falcon 9s, multiple sets of Merlin engines. And then we have here the Chinese launch vehicle, which is wider than the Ariana rocket, but nowhere near as wide as Musk's Starship here. And then this is the new SLS rocket, which is NASA's latest version, and actually is much wider. It's almost twice as wide as Ariana 6, the newest Ariana rocket that just came into commission recently. But it's still not as wide. It's still not going to beat out the super heavy Starship by SpaceX. This is Michael Kaplan, of an engineer who did significant work for Webb, said that it's most likely robotics will be a key player in the next flagship mission after Webb here. To really give you an idea of where the scientific community, so we left off the decadal surveys that began in the 60s and 70s that initiated the concept for Hubble, that came to fruition in the 90s, and then the surveys from the 80s through the 2000s that gave the driving official recommendations from the scientific astronomical community to the politicians and the officials that are in charge of funding and directing funding towards scientific missions in the U.S. at NASA, towards creating Webb. Webb was the driving big flagship mission, and now it's the new crown jewel, taking the throne of Hubble. And now that Webb is fully operational and clearly was a success, what that means is that there's going to be, that was a proof of concept that NASA, even though it's billions of dollars over budget and a decade behind, is able to at least not flub the final lap and through the finish line, and now Webb is running its victory lap, and we are eager to see results from Webb, but just as eager to see what's next. In 2010, the decadal survey was titled New Worlds, New Horizons. That was emphasizing the continued motivation and funding for Webb to get it across the finish line. Now, 2021, by the time they wrote this report, Webb hadn't launched, but they knew it was already done, assembled, ready to go. So they were already looking beyond Webb. And its title was Pathways to Discovery in Astronomy and Astrophysics for the 2020s. Its main concepts were reinforcing dark matter and dark energy research and exoplanet research. So continuation of what Webb is doing, and we're just going to be getting better and better images of the earliest, furthest first stars in the universe and exoplanets that might harbor life. And of course, behind all that is the true scientific spirit of trying to find out what's true, even at the expense of the hard-won current theories. So they want to find either a new paradigm of physics, because we're at a crossroads with gravity not being mathematically compatible yet, and there's no equations that can equate or relate properly gravitational forces with the quantum world of the other three forces. So that's always on the new frontier, and we're always trying to understand trying to look out into the stellar nurseries and the cosmic observatories, the laboratories out there that are the best examples we have of how the physics of our universe works at the deepest levels, at the most intense gravities and masses, the fastest speeds, at the most distant, earliest times, across the vastest distances and the most extreme temperatures. And it's to these observations that we have to align our theories. It's not the other way around. We can't force a paradigm on the universe. The universe tells us what is, and we have to understand it, regardless of how much it hurts. Yeah, this was the 7th report, decadal survey released, the 2021 report, searching for exoplanets. And it, what's cool is, like, you don't hear officials at prestigious institutions like the National Academy of Sciences talking about extraterrestrials and breaking physics. They usually are just toeing the line and trying to just inch very conservatively forward in science and physics. And this report is full of what I think is, frontier pushing momentum and philosophical motivation for going bigger and pushing technologies into the future. They're explicitly talking about searching for extraterrestrial life being a real aspect of what drives humanity forward in astronomy and astrophysics. The whole report culminated in their recommendation, just like Hubble was in the 70s, Webb was in the 90s, and now it's the LUVOIR or HABEX or maybe a LUVEX combination of two different space telescopes. The LUVOIR has two different renditions, but it essentially looks like a larger version of Webb. It's a hexagonal mirror segmented primary mirror made up of multiple segments. Webb was, see if I actually put the telescope here. Whereas Webb was only 18 mirror segments, LUVOIR is 30 or 40 mirror segments. Where did I put it? So there's LUVOIR A and LUVOIR B, and the more conservative version looks still like something twice the size of Webb, and then the more extreme version, which could be built, is massive. You see here how it's triply folded right there. And I hope they do a comparison to Webb, but it's the same fundamental design. It has there's what looks like a solar array, and then I'm assuming they'll have a big sun shield unfolding from that. I gotta turn the playback speed up. Oh yeah, look at that thing. And then now comes the mirrors. There's the baffled. It's so long it needs triple jointed baffles, and then it folds together. Look at that. This thing is really cool, but it's the same concept as Webb. So here's a size comparison right here for anybody watching. Look how much more massive Webb is than Hubble. And then LUVOIR B is Webb is 6.5 meters, about 21 feet, and LUVOIR B is 8 meters, so it's appreciably larger, but not amazingly larger. So there might be some movement upward. But then LUVOIR A is 15 meters, almost triple Webb's surface area of the telescope. It's just beyond massive. It looks like it probably has 100 mirror segments, about 2 or 3 of which is about the size of Hubble. So 30 or 40 times, about 20 to 30 times the capacity of Hubble, if we can even imagine that. And in case we can't, because I can't, here's an example of something Hubble has observed and what they project the LUVOIR B and then LUVOIR A even to be able to add even more detail to. And here it is fit in the rocket fairing of what looks like a starship. Here's what it would look like in the starship. So it's really a bright future, guys. I didn't want to bum you out with a cataclysm talk there for a minute, but if you weren't excited enough about that, even the ground telescopes are getting massive. Right now, the Very Large Telescope Array in Chile are the largest telescopes operating. They were built in the late 90s, and for 20 years now they've been the largest ground-based telescopes. This, other than these segmented ones here, I guess, but the array together creates a really massive primary optic. Each of these are a little bit larger than Webb, but then look at this. At the end of 2029, we have what's called the Giant Magellan Telescope, which is, instead of 4 about Webb-sized primary mirrors, we have 7. I don't know, it looks like it's about 60 feet across. But wait a minute, that's not where, we're not going to stop there. The planned 30-meter telescope, almost 100 feet across, in Hawaii and Mauna Kea, is planned for 2027. These are right around the corner. You're gonna, get out of high school, get out of college, have a kid, be at a job for a few years. You're gonna turn around and read headlines about these 100-foot wide telescopes. This is just amazing. Amazing. And the final note to end on here is what's called the Extremely Large Telescope being built in Chile, planned for before the end of the decade. This is the one I referenced before. Here's the Magellan with a truck next to it. Just to give you an idea, a semi-truck it's measurably larger than an entire 18-wheel semi-truck. And by the way, they shipped this thing onto the top of a mountain in a remote desert in Chile. And also in Chile, this is by far the most remarkable invention of or engineering feat on the ground, at least in astronomy. I don't know, maybe in particle physics they'll have something even more amazing, but this is the Colosseum right here. This is the Extremely Large Telescope in Chile. It's going to be almost 300 feet high. It's going to take you 30 minutes, apparently. I was just reading this a little bit ago, to walk from the front door of the building all the way to the top of the towers up here. The segmented mirror array is going to make up, what is it? What's the number? This is unreal. It's going to be 130 feet across, 14-meter diameter secondary mirror. Webb's was only about 2 feet in diameter. So this secondary mirror is going to need to be 14 feet in diameter. And with adaptive optics, it's going to almost, although it won't be able to read the further infrared bands that Webb is able to do. That's why hopefully LUVOIR will have that, that's what the IR at the end of LUVOIR stands for, infrared capability. But this is going to be, in terms of Hubble, it's going to produce images 16 times sharper than Hubble. It has 256 times the light gathering power. And, man. Yeah, there's tons of other things coming up Something named after Nancy Roman Grace is right around the corner too. This decade is going to be just overflowing with discoveries about the universe, about exoplanets, and hopefully alien life. I don't know what better note to end on. Thanks for watching, guys. And really, thank you for all my Patreons, supporters, all of you guys leaving comments all the time. You guys mean the world to me, and it encourages me immensely. So thanks for all the love you guys always send my way. Hope you guys have a good one, and we'll see you next time. Thanks for watching.